Ashwini, you can start.
Yeah, Ashwin ma'am, you can start.
Yeah, okay. Good evening, one and all. Welcome to day 3 of our workshop, AICT sponsored online ATAL FDP on Geo-AI. On behalf of DY Patil deemed to be University, Ramravadik Institute of Technology, I welcome you all for today's session. It's been an incredible journey so far, filled with thought provoking discussion, shared insights, and valuable learning experiences. Today, it's a privilege to have us with Dr. B.S. Dayasagar. Dr. B.S. Dayasagar is a professor of the System Science and Informatic Unit, SSIU, and head of the Indian Institute, Statistical Institute, Bangalore Center. Sir received his MSc and PhD degree in geoengineering and remote sensing from the Faculty of Engineering, Andhra University, Visakhapatnam, India in 1991 and 1994, respectively. He is also a founding head of the SSIU. Earlier, he worked in the College of Engineering, Andhra University, and the Center for Remote Image Sensing and Processing, CRISP, the National University of Singapore, in various positions from 1992 to 2001. He served as associate professor and researcher in the Faculty of Engineering and Technology, FET, Multimedia University, Malaysia from 2001 to 2007. Sir has made significant contribution to geoscience with a particular emphasis on developing spatial algorithm meant for geopattern retrieval analysis, reasoning, modeling, and visualization by using mathematical morphology and fractal geometric concepts. He has published over 90 papers in journal and has authored and guest edited 14 books and special theme issues for journal. He authored a book entitled Mathematical Morphology in Geomorphology and GSI CRC Press. He co-edited two special issues for IEEE Journal of selected topics in signal processing and applied Earth observation and remote sensing in India. His book, Handbook of Mathematical Geoscience, Springer Publishers, crossed 1 million downloads. His two, his two-volume encyclopedia of mathematical geoscience was released in 2023. He was elected as a member of the New York Academy of Science in 1995, as a fellow of the Royal Geographical Society in 2000, as a senior member of IEEE GRSS in 2003, as a fellow of the Indian Geophysical Union in 2011, as a fellow of the Indian Academy of Science in 2022, and the Indian National Science Academy in 2024. He has also been a member of American Geophysical Union since 2004 and a life member of the International Association for Mathematical Geoscience, that is IAMG. He was awarded the Dr. Balakrishnan Memorial Award of the Andhra Pradesh Academy of Science in 1995, the Krishnan Medal of the Indian Geophysical Union in 2002, the Georges Matheron Award 2011 with lectureship of the IAMG and the award of IAMG Certificate of Appreciation in 2018. He is the founding chairman of the Bangalore section IEEE GRSS chapter. He has been appointed as an IEEE Geoscience and Remote Sensing Society Distinguished Lecturer for 3 years from 2020 to 2024. He is an AJU Honor and Recognition Committee HRC member. He is on the editorial board of Computer and Geoscience Frontier, Environmental Informatics, and Mathematical Geoscience. So it's really a great honor to have such an eminent personality with us. A warm welcome to you, sir. Now I request Dr. Daya, sir, to hand over the session, and over to you, sir.
Thank you, ma'am, for your introduction. Yeah. So now I'll share the screen, and I don't think I can see the other people when I make my presentation. And then I'll start it now, and then I'll share the screen, and then I think it takes it, though it is given about 90 minutes slot. Probably in an hour I'll finish it, and then if there is any interactive things, and I can
Yes,
yeah,
sir.
1 hour
Yes, sir.
15 minutes, and then I'll see. Yeah. Okay,
Yes, sir.
then
After session, we will put the question answer session.
yeah, that's fine. And if someone wants to stop me and ask me, and then I don't know how to do that, and someone can really
You will
mention
get
that.
a voice signal. Someone has a doubt, then they will directly talk.
Yeah,
They
yeah,
will raise the signal, yeah.
yeah. Okay, thank you. I'll just share the screen, and then I'll start. Yeah.
Yes. Yes.
Not this. Can you all see the screen?
Yes, sir.
Yes,
Yes,
sir,
sir.
yes.
Yes.
Yeah. So this is the topic that I have been talking for the last so many years, and so I'll try to make it simple. And this is mathematical morphology in spatial data sciences. And you'll all realize that there are more illustrations. There are more illustrations. I will try to skip most of the equations. This mathematical morphology is a small theory, but it has wide-ranging applications. And this it's about a simple mathematics to study shapes and functions, and to study the characterize quantitatively characterize the geometric structures of any spatial objects or spatial functions, and that rely on set theory, lattice theory, random functions, and topology. And so very basic set theory would really let you know that this mathematical morphology is not that difficult for any engineer to really venture into. And as we all know that we all deal with a lot of remote sensing data and also spatial data and geographic information science related data. So the moment you talk about, I'm in a lecture, please. Sorry, and sorry, this and this the moment we talk about the science of where, and so that's where the geographic information science comes into picture. And that science of where means the spatial coordinates, and we call them as latitudes, longitudes in a geographic language, and so xy spatial coordinates in any other engineering context. So to be frank, that this mathematical morphology is very popular in not only in geosciences. Now geosciences, now it's seeing a lot of applications from mathematical morphology and geostatistics, but it is more popular in image processing and image analysis, and of course computer vision. And so nice to see that there is a topic of geo artificial intelligence, innovations in AI for improved spatial data processing. But when we spend a lot of time in retrieval of information, and we ignore about quantifying the information, and reasoning the information, and then modeling and visualization. And we spent a lot of time, almost 90% of our time and money is getting into retrieval of information. But is that just sufficient? This is what I used to argue a lot during my lectures. And to tell you and why and what. And so when we talk about any dynamical system, and these are the specific words, like when we talk about a dynamical system in the language of physics, and we talk about dynamical behavior in the language of geography, and we talk about spatiotemporal models or behavior of a specific system, how it behaves across spatial scales and temporal scales. And for that, the moment you have a reasonably well acquired data, and how to process that data, and to retrieve important information. And once the information is available, information, I say that information is our maps. And so, how to analyze that, and then how to reason that data, and finally, for the kind of developing a spatiotemporal model, I'd put it in a slightly different way. Retrieval, analysis, reasoning, modeling, and visualization are the main ingredients of any spatial data sciences. So, all these four or five ingredients that I spoke, is there a good mathematics to really handle those ingredients? And I could find out that mathematical morphology is an area of geoscience that most people don't realize will literally change the way what happened. And this, are you able to see this?
Yes, sir. Yes,
So
sir.
you are
No,
We're
it's
only able
slides
to
are
see the
not
first slide.
I am unable to move the slides. I'm sharing it once again. Yeah, now you are able to see, right?
Yes, yes.
Yeah. So this is a that most people don't realize will literally change the way they look at Earth. And so I have seen that this mathematical morphology can handle all the ingredients of spatial data science. And so in mathematical morphology, I think some of you are quite familiar that the data will be investigated with another data. That another data, typically we call it as B or G. And if it is B, and we are typically referring to a kind of planar structuring element. If it is G, we are referring to a kind of structuring function, which can also be termed as the probing rule. And so a data will be investigated with another data. And typically the data that I always love to explain some of those algorithms that we developed in over almost 2-3 decades is the digital elevation models. I must say that digital elevation model is an engineering marvel, an important source of data for both geoscientists and planetary geoscientists. And so there was some kind of earlier studies using mathematical morphology. It was applied on binary and grayscale images, and now people have been using multispectral images and hyperspectral images. Typically, the morphological distances will be really useful for band selections. If somebody is interested out there to deal with band selections from a large number of bands. And this is some background review, and I would skip it. And as I already mentioned, that retrieval, quantitative information analysis, information reasoning, and simulation and modeling of spatiotemporal behaviors. And at the end, spatiotemporal behavior, can we really think about a system specific attractor? And so the moment the attractor is there, that attractor should tell us and how that particular system that we have been showing some interest will behave. And typically it is a kind of predictive analytics. And to show you in one single slide that the results of morphological algorithms that we have, I'm going to show in the subsequent slides. Or look at this, this is a kind of synthetic digital elevation model where all brighter regions are higher elevation regions and darker regions are lower elevation regions. In between all the shades are the intermediary elevation regions. And this is just shown to explain you that it is not so colorful like many of the other hyperspectral images, and it shows a kind of a simple grayscale image, but it has a rich amount of geometric, morphologic, and topologic quantities. And what are they? Broadly, the two topological quantities that one can derive from this particular digital elevation model are, it's not so clear here, green lines and blue lines, but in the subsequent slides you can see that. And green lines are the valley connectivity networks and blue lines are ridge connectivity networks. How to extract those things? We have some a nice commercial software, so through by using which you can extract ridge and valley connectivity networks very nicely, but they fail to really perform well when you take a kind of the digital elevation models from rather gently sloped regions. So to confirm further, and if you take a digital elevation model of some kind of Himalayan regions where the terrain is very hilly, and your algorithms will work very fine and which are available in commercial softwares. But as you come down to the the mouth of the river or the floodplain regions, and those DEMs have very gently sloped regions and where you don't see the intricacy, and that is the time and many of the algorithms or the techniques that you employ from the commercial softwares will fail to produce proper ridge and valley connectivity networks. And that is where we have given an algorithm strictly based on morphological skeletonization. And so how we have employed morphological skeletonization to convert the given data set into its ridge and valley connectivity networks. And then once you have a DEM, and partitioning that DEM in a meaningful way, in the meaningful way for many of geoscientists and remote sensing specialists, and is a biogeographic boundary is the meaningful way of partitioning the given data. So biogeographic boundary, and we take all regional minima and treating all regional minima as kind of water bodies, because water bodies are formed at the topographic depressions, and that water water will get collected at the topographic depressions, and if you allow them to flood incessantly, and then so the flood propagation front lines, they extinguish at multiple points, and so those things that is where you construct the dam, and you can really get the watershed partitions, subwater partitions, and that is what is actually shown in this particular picture. So this is one case I would like to show in subsequent slides, and what is the simple math behind it, and explain that. And then the next one is about, another part of the retrieval that I would like to show is when you have a large number of images in a kind of database. So assuming that those images are digital elevation models, and to give you an example, this is a DEM, and deliberately I made this into 4 quadrants, quadrant 1, 2, 3, and 4, and which 2 quadrants are close to each other, which 2 quadrants are farther from each other. And I would say that I wanted to pair those DEMs, and this will really help you to group the given data available in your database. And so what is that we have employed? We use some morphological distances, and so those morphological distances include morphological dilation distance and morphological erosion distances. And so using those distances and simple other operations like infima suprema ratios, and then those distances, we can compute the rank for any kind of pair of images. If you take this pair, and what is the rank? If you take these 2 images as a pair, and what would be the rank? And so best pair to worst pair, you can actually categorize them, and then that will work like a kind of clustering or grouping the given data sets. So that is another case I will show. These two are from the retrieval part. In the analysis, once you have information, assuming that this is a DEM, this is indeed a DEM. And so what is the roughness of this particular DEM? This is a watershed DEM, there is a boundary. And then what is the roughness of that? And so for that, we typically use a morphological granulometries of the foreground roughness to quantify the foreground roughness, and morphological anti-granulometries to quantify the background roughness. And what we do, and we keep on performing some shrinking and expansion operations. And so as by allowing this particular watershed DM to lose its energy, that energy, you can see that it is going from the brighter to darker. And so as it is
That's,
going
that's right.
yeah.
Bro, are you changing the slides? We are not able to see the slide change.
No, the same slide I'm showing. In one single slide
Okay.
I'm explaining it, but you are
Okay,
able to
sir.
see the cursor, right?
Yeah.
Yeah, so this cursor, yeah. So this
Sir,
is going
can
from the full energy level to, as it is energy is getting depleted, and energy is nothing but the sum of all the grayscale values. Here the grayscale values denote the elevation values or the mean sea level, and so that is how it is a digital elevation model. And so for every data set, and there is a foreground and background. So what is the foreground roughness and what is the background roughness? To quantify the foreground roughness, we perform multi-scale opening operations. And so to compute the background roughness, we perform multi-scale closing operations, and here it is losing energy and here it is gaining energy. And then I will show how with a simple symmetric structuring element we can compute the global roughness values, and global roughness values of both foreground and background. The moment you change that structuring element into some kind of directional structuring elements, we can compute the directional roughness values. And how to compute the spectrum of directional roughness values will also be explained. That would come from this part, quantitative information characterization. And then this is in a grayscale domain, and when you have some kind of data, that data in the sense the hill slope regions, so the moment you subtract the skeleton, that is reverse in this case, and you will have some kind of non-network space. That non-network space can be packed with morphological shape decompositions, and then you can compute certain power laws which will yield scale invariant measures, but they are shape dependent. So at the end, in geosciences and geography, it is not just the scale but shape matters a lot, right? And that is, this and all will come from that. And then a reasoning part, and you look at this particular panel which is given here, and we have 29 states. Which two states are better interacting in terms of a specific variable? If I speak about the variable trade, so which two states are having better interactions, which two states are having feeble interactions? And so that case I will explain it here, like variable specific classifications of the zones, states, and in a hierarchical manner. And these are some of the best interacting states at the first five top panel are the best interacting states in terms of the trade between the states. And so the lower pictures were shown, and so least interacting states and mostly the exterior states, assuming that Goa and Nagaland, is there any kind of interaction? So that is actually done through some kind of modified gravity model studies. And then for visualization, modeling and visualization, you look at this particular panel, and this is the source DEM. That DEM has become over a period of 10 years, and assuming that it has become like that, and source and target, is there a way that you can find out? Because you have very sparse data here. In 10-year period, you have only two data sets. And is there a way you can simulate how this particular DEM has been traversed to reach to this level over a period of 10 years? You require to have some kind of interpolations. Those interpolations were actually computed by following morphological median computation. And so between this and this, the morphological median is this. And between this and this, the morphological median is this. Between the median and the target, is the morphological median is this. This is a hierarchical process. And then you can actually compute how this visualization can be done by following a simple morphing procedure through computing the hierarchical median functions. This is the overview, and now we all know the data that we are referring has the spatial component. Digital elevation model is one of that examples, and there are many other examples. And if you have interest in simple hyperspectral images, and so that is the spatial data, because we always talk about XY coordinates. And then, as I mentioned, mathematical morphology is a wonderful uh, theory and technique to quantify the geometric structures and functions, so which are typically based on two fundamental operations. I should say that erosion to shrink and dilation to expand. Whether you are performing binary erosion dilations or grayscale erosion dilations or graph-based erosion dilations. And so these are all certain advances that we can see. And so just by using erosion dilations and their multi-scale versions, the skeletonization is the transformation which can convert the given data into unique networks. And then ranks for pairs I have already shown, and as a simple example in the previous slide. And then it involves, simple morphological distance calculations. And then next one is the quantitative information analysis, granulometries and superficial roughness, characterization and quantification. Quantitative spatial reasoning, again, morphological distances in spatial optimization and spatial interaction modeling. There are two subcases here. And the last one being the modeling and visualization, like morphological interpolation to convert the point data into polygonal form. Like, for instance, many of our geographic data or meteorological data will come from the point sources, and so from meteorological stations. And so when that point specific data is available at specific points, and can we convert them into kind of a zonal map? And so to do that, and there are some weighted skeletonization by influence zone mapping technique, which is also coming under the interpolation families, and then morphing of source DM into target DM. And then the last one being the way forward. How do you use this retrieval analysis, reasoning, modeling, and visualizations to make some kind of predictions about a specific dynamical system that you are targeting? So this is an education opinion piece, and so many people they look at digital elevation model, they feed into kind of software, and then they want software to do the analysis. But if those who are with a bit of mathematical knowledge, particularly coming from either mathematical morphology or wavelets or discrete geometry or uh, some kind of fractal geometry, if they have that kind of mathematical knowledge, the way they look at digital elevation models, it shows a lot of hidden features of geometric, morphologic, and topologic significance. And to unravel those hidden features, and I have how mathematical morphology will be of great use. And also to tell you that the digital elevation models, billions of dollars were spent in generating DEMs, but they were not being, utilized to their fullest extent. And so, having some kind of mathematical knowledge will really help you to really tease the DEMs in a proper way. So these are some of the DEMs just to show you the. This is a synthetic DEM I have already shown, and this is a topex poison DEM, which was actually of the region Malaysian region. And so this is a digital bathymetric map, and which was acquired through ground penetrating radars. And then this is our Cartosat DEMs, and so there is a SRTM DEM. And so this is the DEM that we generated by taking the contours from the topographic map. And so at different vertical exaggerations, and from sparse data to denser data, how to handle that. And you have coarse resolution DEM, and how to convert that into super resolution DEM. That is possible through morphological interpolations. So this is just to say that what is the science out of DEMs that you can really derive. And so the spatial data, what does it have? And so as I mentioned, the DEMs are, you can also call them as uh, a kind of spatial functions, and we call them as a simple f of xy. F of xy is equivalent to z, and then the z value is the elevation value in our DEMs, and it has a rich amount of geometric, morphological, topological quantities. And the relevant mathematics is morphology that I have been using. The science out of spatial data and spatial information, all these are the features that you can really, features are parameters that you can either derive or compute and from DEMs. And if you can really partition the DEM initially into kind of biogeographic boundaries, and then if you perform or calculate or compute all these features and parameters, and so when you do that for multiple DEMs of different time periods, and we can really derive the behavior of the terrestrial surfaces. So to give you a background, like these two are, Georges Mathron and John Serra were the founders of mathematical morphology, and they also did a lot of work on geostatistics. I should say that there are two schools of thought, and one school of thought thinks that spatial statistics was given by Ronald Fisher, but another school strongly believes that Georges Mathron is the person who is the father of spatial statistics. But so in addition to spatial statistics, they also spoke about the mathematical morphology, grayscale morphology, graph mathematical morphology, and adaptive mathematics. I have listed many operations and transformations here. I don't go into all these things because so to teach a kind of 3 credit hour course on mathematical morphology and applications, it takes about 26 hours of lectures. So to just give you very quickly browse through, these are the notations. XMB are the spatial objects or sets, and then f of xy is a kind of DEM or the spatial function. So area under F is a kind of energy under the given function, and B and G are the flat structuring elements and non-flat structuring functions, and Fi and Fj are the two spatial functions of two different time periods. And so these are required to understand the subsequent slides. And this is a dilation symbol, this is erosion symbol, and dilation followed by erosion is called closing, and erosion followed by dilation is called sir, I'm giving a lecture. Can I call you back, sir? Hello. Yeah. Sorry. Yeah. So, and then these are the two spatial sets, xi and xj, and the intersections, their unions, or when you talk about these spatial functions, we call them as infima and suprema. And so these are all some basic notations. And then their operations are x erosion by b, and x dilation by b, and x open by b, and so x closed by b. And then so they're multi-scale versions using nth size b, and then you can perform multi-scale erosion, multi-scale dilations, and multi-scale openings and multi-scale closings. And these are all wonderful nonlinear filters. And then the moment you extend that to grayscale cases, as is the case with our digital elevation model, so erosion, dilations, and openings and closings for grayscale images, and so both opening and closings are very robust nonlinear filters, and which were proved very robust when you talk about removing the speckle noise from the images, and alternative sequential filters. I know that many of the people in the audience, they are all engineers, and they understand digital filters and alternative sequential filters and adaptive filters. And so morphology offers numerous things, particularly to look at those filters in nonlinear fashion. And their multi-scale versions like erosion by multi-scale B of various different sizes, and ranging between 0 to capital N. And these are the some background And these illustrative examples, I think these are all some textbook matters, and I'll just skip it. And then the skeletonization, what exactly is this? Erosion of a set X, and the same eroded version, if it is opened by arbitrary size B, and it actually filters certain, sharp peaks. And this is to extract the nth level skeletal subsets. Once you have all nth level skeletal subsets, if you take the union of all those nth level skeletal subsets, you get a kind of skeleton for the object X. And can that be performed on any function? And that is shown here. And one way is to convert the spatial function into all possible binary images like threshold elevation regions from digital elevation model, perform the binary skeletonization and systematically unify them, you get the skeleton network of the spatial function, which is nothing but the river network of within the digital elevation models, right? And similarly, you can also compute the distance between the spatial objects. And many a times the distance between a spatial object xi and the spatial object xj, it doesn't necessarily be the same as xj to xi. If the xi and xj are spatial objects of two different sizes and shapes, and the distance is a kind of directional, and then from a to b is different from b to a. And so in the same way, when you perform we have dilation distances and erosion distances. I don't go into the details, but these slides I will leave with the organizers, and so they can understand the properties of the set properties, how we are performing a kind of operation to compute the distance between spatial object A to spatial object B. And so there, once you know the distance calculations, and you can also compute the median between the given two spatial objects. Median is nothing but take the intersection of object A and object B, take the union of object A and object B, and then intersections will be dilated and union will be eroded, and then take the output, the intersection of those two outputs, and do that process for all possible n's ranging between 0 to capital N, and then take the union, you get a kind of median between the two spatial objects. Same is true with the spatial functions. And so how do you compute the median function between the two spatial functions? It is like, as I have shown, the source DEM and the target DEM, or the DEM at 10 years back and DEM currently. Can we really simulate all possible intermediary interpolations between 10-year back DEM to the current DEM? That can be really done through recursive median function computations, and which is through this. And instead of intersections and unions, and we follow infima and suprema, and then grayscale dilations and grayscale erosions. So with this the mathematical morphology background introduction is over, and now you look at and how we computed the ridge and valley network extraction. First, you have a digital elevation model. You can convert them into all possible thresholded elevation regions by simply thresholding it, and you can get fi plus 1 and up to all possible grayscale decomposition that you do, and you call them as some xt and xt plus 1. And so if it has let us assume that 255 grayscale values here, and at the most you can decompose that into 255 grayscale no thresholded elevation regions. And so one of the thresholded elevation region is shown here, and so this one is converted into its skeleton. As I explained the skeletonization equation previously, and you compute erosions with nth cycle, and so all nth cycle erosions were opened. This is just to smoothen from inside by arbitrary size B, and then you get the skeletal subsets. And so taking the union of all the skeletal subsets, and you get the skeletal network, which is something similar to this. And the same skeletonization you can also directly perform on the grayscale DEM instead of decomposing them into thresholded elevation regions. And you also get a kind of proper connectivity network, but always doing it on a binary domain, and you get better connectivity within the network. And so this is typically a potential valley connectivity network, which is also the kind of flow paths for the streamlines within this kind of DEM. So you can see this in this particular picture, and so this is a DEM, and then you have green lines and blue lines, and green lines are the river networks, and the blue lines are ridge connectivity networks. You know that ridge connectivity network is surrounded by the valley connectivity network, or you can say valley connectivity network is embedded between the ridge connectivity network. And so their partitions, as I mentioned, you can compute the regional minima. There are many regional minima, and then allow those regional minimas to flood with uniform speed. And then wherever those flood water front lines, typically the dilation front lines, extinguish each other, you construct a dam. That is how we have partitioned this particular DEM into multiple watersheds, ranging from fifth order basins to the first order basins, and so they are all there in that particular partitioned digital elevation model. So this is just to show you from a simple, I would say this is a fractal basin, and that basin can be converted into its skeleton, and we have given certain order designation here. So why we are doing that, and we have to quantify or characterize the morphometric properties of this particular watershed fractal basin. And then once you have the network, when you try to reconstruct the original object, and those features can be assigned with certain kind of color codes, and then we can get this kind of two-dimensional, I would say, a spatial object is converted into spatial function, and you can treat in internal color regions at the topologically prominent regions, which are nothing but our hill slopes and hill valleys, right? And then it is showing that in a kind of vertical exaggeration form, and this is shown like a kind of typical landscape within a watershed. So all this is possible with mathematical morphological operations. What is involved here is simple skeletons, and then reconstruction of the original object from the skeletal subsets, and then assigning certain color codes of the gray shades when you are reconstructing from the skeleton, and then you can convert a simple black and white object into a kind of digital elevation model. It is like converting a kind of spatial object into a distance function. Right, and then another subcase in the retrieval part is ranks for pairs of images. I don't go very detailed here, but the end equation is this. When you have two spatial functions, and how good are that particular that particular pair. Let us say Fi and Fj are the pair of images or the digital elevation models, and are they close to each other? And then how close they are, can you give a specific rank? The rank of one is the best pair, so rank of towards zero is the worst pair. And so to compute that, what we have done, we take the infima between the ith image and jth image, and infima is nothing but the point wise minimums, and the suprema between ith image and jth image, this is a point wise maximum. And then take this corresponding areas, and sum of all those point wise minimum values between I and j, its corresponding area, and so its corresponding area for the suprema, and take the ratio. If fi and fj are exactly similar to each other, obviously this ratio will come as 1. And so if it is otherwise, you see there is a kind of this particular ratio will range between 0 to 1. And so 0 is completely different from that ratio of infima and suprema things. And then we compute the erosion distance between I and j, dilation distance between I and j, and minimum of those two erosion and dilation distance will come in the numerator. And so maximum of this erosion dilation distances between I and j will come as the denominator, and then take the ratio. This ratio will also range between 0 and 1. The product of these two ratios will get you the kind of rank matrix, rank interaction matrix. And how do we compute the distance between I and J? So we take the infima between I and J, suprema between I and J, and then infima between I and J. We keep dilating this infima until the area of that will be greater than this particular area. So what is that minimum n value that we use on B is the distance between I and J. So similarly, here for the erosion distance, this is the equation. And then, so we have median distance equation also we are given, but I am not covering that. But the core equation at the end is to this. And if this ratio and the product of these two ratios, if it is given 1, if it, yeah, is there anything? Yeah, can I continue?
Yes, sir, you can continue.
Yeah. So yeah, so this particular DEM we made it into 4 quadrants, and we made it into 4 quadrants, and that particular ranks we have computed, and we have 4 quadrants: F1, F2, F3, F4. F1 to F1 is 1, and F2 to F2 is all diagonal values are 1. But for F1 to F2, that particular rank is 0.8514, and F1 to F3 is 0.65. Like that, we have paid those DEMs, and we said that these 2 quadrants are the best pairs, and these 2 quadrants coming from this particular family are the least best pair and the worst pair, you can say it. So this will help you to, in a crude way, you can group the given data sets available in DEMs, right? So now you have seen so far about information retrieval. Through skeletonization, you have seen the network extraction from DEMs, and through distances and some suprema infima ratios, we could compute the ranks for the pair of images. And then the next one is the quantity information analysis. Typically, this is a granulometries to compute the superficial roughness quantification. You look at here, those who are familiar with morphometric studies, river morphometric studies, they will understand these are the 3 networks which will yield the same morphometric quantities. In a way, these 3 networks are the topologically invariant, but the core geomorphologist wants what is that measure that can show the basic distinction between the 3 networks. And then if you do the network morphometric analysis, you get the same topological quantities like bifurcation ratio and mean length ratio. So in turn, we say that these are topologically invariant, but they can be topologically invariant. Is there any other measure which can really show the basic distinction between these 3 networks? So for that, what we do, take the network and construct the convex hull around that. The way we have done is by recursive multi-scale closings, we can convert the network into its closed hull, which is like this particular patch, and then subtract that network from that convex hull, closed hull, and then whatever you see is the white space is the non-network space. Typically, it is the hill slope regions in a planar form. That hill slope, by leaving the skeleton or the river network, and you work on the non-network space, assuming that this is a non-network space. This is a Napoleon space, mathematically called it's a Napoleon space, and you can pack octagons of various different sizes until the whole space is filled by those octagons of different sizes. So it is shown in a colorful way here. And so what we have followed here, we have followed morphological shape decomposition. Typically that can be done with a multi-scale morphological openings. And so by following that, this non-network space is packed with the octagons of various different sizes. And now we can derive a kind of power law relationships between the number of octagons versus the radius. And then on log-log scale, if you take that relationship and you can derive a power law relationship, and that power law will be scale invariant, but shape dependent. The moment you change octagon to square and you get a different power law, which is scale invariant, but shape wise, it is a different power law value. So ultimately, what matters is not just the scale invariant measures, but the shape dependent measures. right? And so that is what is the morphological shape decomposition for the information characterization, quantitative characterization, right? This is one case. The next case is about on grayscale functions. You take not just black and white like binary images that I have shown, and this is a digital elevation model. And when you perform multi-scale morphological openings of scale 1, scale 40, scale 80, scale 180, 120, and 160, I've shown certain snapshots here for the scale 1. For the scale 1, and so this is what we are doing, one erosion followed by dilation. And this particular panel is 40 cycles of continuous openings followed by 40 cycles of continuous dilations, and so that will make this. And so actually from scale to scale, as you perform with increasing opening cycles, and it loses its energy, and you can see it is becoming darkened and darkened, that loss of information is typically called pattern spectrum. As you all know, for fast Fourier transformations will quantify the spectral content, but this morphological openings recursively in a cyclic form, and it can quantify the pattern spectrum, that is nothing but shape size content in the given spatial function. And then once you get that loss of information from cycle to cycle, from nth cycle to n plus 1 cycle, and so this simple algebraic subtraction will give you the pattern spectrum of nth order. And then once you have that pattern spectrum, the total energy of the original DEM, you divide that the nth level pattern spectrum values with the total energy, you can compute the probability values. And once you have the probability values, you can take the P log P, that is the Shannon's entropy, for all n ranging between 0 to capital N, which is shown somewhere here, I think, which is shown here. And we can compute the uncertainty index. That uncertainty index is also called as granulometric index and morphological entropy and spatial roughness, and which was heavily used in several decades ago for the texture quantification of the images. And when you do that in a converse way, instead of opening, if you perform closings, dilations followed by erosions, and cycle 1, cycle 40, and up to cycle 160, and you can see, rather than losing the energy in the case of as you have seen in the case of computing the foreground roughness, and you see the gaining of energy here, and those set of pattern spectra values can be computed like this. And cycle 2 closing of the spatial function with respect to b of size 2, and so b of size 1, and then if you subtract that, you get the gained information from cycle 1 to cycle 40. And then in the same way, you compute the probability values, and then uncertainty index, you can compute the background roughness. These foreground and background roughnesses are again the shape dependent. The structuring element here is a rhombus, and structuring element here is a square, and structuring element here is an octagon. You mind you that dilation of rhombus with a square, you get a kind of octagon. And there are relationships, and establishing these roughness values, the relationships in terms of roughness values is a very interesting study that one can really venture into. So this and all you have seen with a compact symmetric structuring element. This is a rhombus, this is a square, where the origins are at the center, and then this is an octagon. But if you perform these granulometric operations in a way that they are one directional, one dimensional structuring elements, you can see this is a single line, and this is another single line, this is another single line, this is another single line. You call them as b1, b2, b3, b4. If you take the union of b1, b2, b3, b4, you get a square kind of structuring element. We have performed with all these 4 different directions, and those granulometric index we have computed. And it is not just the roughness based classification, directional roughness based classification, in what direction the roughness is very high, and so we are giving in that particular hatching symbol here, and in what direction roughness is very low, and high directional roughness based classification, and low directional roughness based classification. We have shown these things, and which has lot of applications in geophysics and seismology. And then so this has to be validated further, and we are giving just values, and then whatever the results that we are getting we are showing. But validation is very important if you have certain kind of because there was a study by someone recently, and after the earthquakes, where there will be large number of aftershocks. So it is linked with the complexity of the terrestrial surface. The terrestrial surface is very complex, and the aftershocks will be more. If it is less complex, and the aftershocks are rather less. That is a confirmed study. And to link that kind of statements and inferences with the directional roughnesses will be an interesting study further. So these are some of the snapshots. What will happen? This is a lower Indus Basin DEM. So this is with after multiple multi-scale openings by 10 cycles of opening, and by 100 cycles of opening, by 1000 cycles of opening, and then 10,000 cycles of opening. How this terrestrial surface is changing. So after all these erosions and dilations can be treated as a mimicking process of so erosion to shrink, and dilation to expand. And there are ways to really link that with tectonic and weathering process, endogenic and exogenic process. And for a small watershed we have taken, and you can see with the 0 cycles, 200 cycles, with a simple B of a symmetric nature, and how it behaves, and with a B of a B1 type, which is a directional. And when we change it from symmetric to directions with B1, B2, B3, and B4, and you can see how the terrestrial surface is behaving. And so this is very interesting. If we can really bring some scientific outcomes of after performing these terrestrial surfaces. And so these are also with multi-scale openings with B1, B2, B3, B4 on this the entire lower Indus Basin. These are with simple small watersheds, and where you can really see the conspicuous variations from structuring element to structuring element. So this is what I have explained on granulometries and superficial roughness and characterization. And one is through the simple morphological shape decomposition when your data is a simple hill slope data or a river network data. So the grayscale granulometries that we have used when you are using the data as a kind of spatial function. And then the next one is a quantitative spatial reasoning, and where the morphological distances are very useful in spatial optimization. Here also I'll show it mostly on a kind of uh, I'll skip most of these things. Look at this simple synthetic image. There are so many streets here. And if someone asks you which is that state, which is strategically located, in the sense from that state reaching out to all other streets is possible with a minimal energy expenditure. So that is the simple definition of the strategically located state. And the distances are like this is one object and this is another object, and computing the dilation distance is nothing but you keep on expanding this until this becomes a part of it, that dilated version. You can see all these green lines are the dilations of this particular AI. And so until it occupied this one. And how many number of dilation cycles will be taken? That is the dilation distance. The same way you keep on dilating this until A1 becomes, AI becomes a part of the dilated version of AJ. So that is the dilation distance. You will realize that the dilation distance from AI to AJ is different from dilation distance from AJ to AI, because these are of two dissimilar sizes. If these are of same sizes and shapes identical, and the distance between AI to AJ and AJ to IA will be the same, right? That is the idea. So, oh my God, yes. Okay, so these animations are creating problem, but I can show you that you see this is a Landsat image, and there are so many conspicuous water bodies in blue shades, and those water bodies were traced here and which are shown in black and white here. And for all these water bodies, you can compute a kind of zone of influence map, which is nothing but you keep on flood them and until they reach to some extinguishing point, and then you get a kind of skeletonization by zone of influence here. And these are the actually zonal maps. And so for these water bodies, and if someone asks you which is that water body strategically located, so that people can, when there is a drought in other regions, they can reach out to that particular water body and fetch water. Or governments can really protect that particular water body if there is a crisis with financial crisis. So that one, what we do, there are 66 water bodies, and so from every water body to every other water body, you can compute the dilation distances, and then so you get a 66 by 66 distance interaction matrix, and then you can compute which is that water body strategically located. It is nothing but in that interaction matrix, the column wise maxima you compute, you will get 66 column wise maxima values, and minimum of the most minimum of all those column wise maxima values coming from which water body, and that is the water body strategically located. That is how I say that this is a kind of spatial optimization. And then which was also done on this, their zones of influence, and then this is the strategically located zone of influence. And so the similar idea, we have used it in slightly different context. That context is you can see that the next slide. I think there is animation. It is taking time. My God. I will share it again. I think I have to share this. No. Okay. And this is a kind of gravity model. And so simple Newton's gravity model, mass of xi and mass of xj, a product, and then distance
Excuse
square
me,
between.
sir.
Can you
Your
can you?
first, your first screen is visible. Title page.
Oh, so you cannot see this.
No, no, we are not able to see your slide number.
I have stopped sharing. Probably I will. I will. I will use.
You can do entire sharing.
Yeah. So I have done that, but now what I do? I think best thing I will use the PDF file because of the animations. It is creating problem, and edit view document as a full screen mode. You can see this, right?
Yes, sir. Yes, sir.
It's moving.
It's
Yeah,
getting
I
close.
think this I will skip those animations are creating problem. Yeah. So this is the one I'm talking. So this is a simple Newton's gravity model. So assuming that xi and xj are the two states, like spatial objects. And so what is the interaction between those two states? Assuming that you have some kind of trade between those two states. And so, or you'll take some kind of, land values of those two states. And then will there be a good interaction? Because as per the first law of geography, neither things are well correlated and the farther things are less correlated. I would say that correlation is a kind of interaction. And so for this one, what we mentioned in social gravity model, and so this interaction between x and j cannot be symmetric. Probably in celestial mechanics it can be symmetric, but in social gravity model, we feel that, as we have also seen, I to J distance is different from J to I, and also the objects have states have some kind of strategic importance, and exterior states have rather less advantage, and whereas the interior states have a lot of advantage because of the location significance. So in turn, we have given a kind of interaction, force of interaction between xi and xj, and the distances are direction specific, and then location significance of xi and xj. By introducing this and then direction specific distance, and we made this gravity model as a modified gravity model, where xi to xj interaction is different from xj to xi interaction. So for that, we have given all distance interaction matrices, and then the product of location significance indexes, and then the mass of the land values of the xi xj, and the level of interaction matrix at the end. So you can see that how they change, and so I will skip this equation, but you can see it here. And so this is a kind of spatial system, and in which this is a kind of a subsystem, let us say, or this is the spatial system. You have so many states, and those states, which two states have better interaction? This is Chhattisgarh and Orissa, and this is Madhya Pradesh and Uttar Pradesh, and then Uttar Pradesh and some other states. So, like Uttar Pradesh and Chhattisgarh or Orissa, like that, these are the best interacting states. And I could not show this animation here, but it will show that initial animations are the better interacting states, and as the time progresses, and then exterior states are least interacting states. Ultimately, what matters is the distance, and if the states are next to each other, and the kind of interaction between state A to state B, and then state B to state A, though they are not symmetric, they are better interacting states. And so this is what we have done with mostly for geographic information audience. And you can see the more details in this particular paper: variable specific classification of zones, pairs of zones, and clusters of a spatial system via modified gravity model in IEEE transactions and emerging topics in computing. So which was published a few years ago, and just see that, and then if you have interest in GIS. And then further, the next case is about modeling and visualization. And one of the things is, I mentioned, when you get the point specific data, we have some 35 rain gauge stations where we got some kind of rainfall values. And those rainfall values, at times when you were putting it in a kind of decision support system, you require the data to be in a kind of polygonal form or a zonal form, in a contiguous form. And to convert this point specific data into contiguous polygonal form, and we have performed weighted skeletonization by zone of influence techniques, that is WSTs. Exactly what it is, and it involves a few parameters, like to construct a zone of influence for one specific point, how to do it, and which was given here. I don't go into those details, but there is a paper that can be seen, cartograms via mathematical morphology information visualization. You have every step explained of within this equation, and it is like this. And so this is also a cartogram. It is not just converting the point specific data into polygonal form. You look at this is before Andhra Pradesh was bifurcated, and there are 4 states here, like Karnataka, Andhra Pradesh, Kerala, and Tamil Nadu. And if these 4 states, if they have to be visualized, we call this particular map as a area projection map. What is the variable representing this cartogram? Variable is the area within the boundary of the states. Suppose that variable is changed from area to, let us say, crime rate. The crime rate, let us assume, that is very high in Kerala and very low in Andhra Pradesh, and then it has to be shown much smaller, and this has to be shown much bigger, without losing the adjacency and the overall shape. So for that, we have given 4 or 5 different possible ways of converting that into cartogram. That is called variable specific cartogram. And so I'm referring about crime rate, or suppose the groundwater yield is very high in Kerala. It has to be shown much bigger. Followed by Karnataka. It has to be shown slightly bigger than that. Followed by Andhra Pradesh. It has to be shown slightly bigger than this one. And at the end, and so the groundwater yield is very low in this particular Tamil Nadu, and then it has to be shown much smaller. So these are some of the things, and what we do is we perform a weighted skeletonization by zone of influence. It is like you have multiple water bodies. What are those water bodies here? Typically the state centroids, and allow them to propagate with speed proportional to the variable strength. If the variable strength is very high, and you have to propagate it much faster, and which can be seen here in probably these blue lines, and followed by yellow lines, followed by green lines, and followed by this particular maroon lines. And so, if you impose certain kind of propagation speeds, which are proportional to the variable strength at particular that state, and you can convert that data into kind of cartogram form. The way forward in GIS research, geographic information science, is modeling not based on the choropleth maps, modeling based on the cartogram, variable specific cartograms. If you have variable specific cartograms for the variables, let us say groundwater, rainfall, runoff, and all those different variables, and then those cartograms and how to integrate and then give you a kind of spatio-temporal model is a kind of completely different kind of spatial statistics we are talking. So that is just an idea, but it has not been attempted so far. So after this, that is also a kind of interpolations. Whatever we are doing here are kind of interpolations, and converting the point specific data into polygonal form, and then or converting the data into kind of variable specific cartograms. And you can see both of these papers, one in GRSL, one in information visualization. You will understand those two things. And then the next one is simple morphological interpolations. Again here, between the spatial objects, between the spatial functions. And spatial objects are obviously in binary form. Spatial functions are in grayscale form. So you look at this. This is the typical median set computation. You have xi and xt and xt plus 1, and their intersections and unions. Intersections are dilated and unions are eroded for lambda value ranging from 0 to some capital N value. For all lambda values, whatever the outputs that you are getting, take the intersection. You can actually compute a median object between object xt and xt plus 1. Assuming that t and t plus 1 are two different time periods, and an x is a kind of water body, and that water body is over a period of time, it has changed its shape and size, and then you don't know how that water body at the intermediate time between t and t plus 1. And if you want to predict that, and you can compute this median. So how we have used that is, we have successive contour lines in a topographic map, which we call them a very sparse. And to convert this sparse contour data into denser contour data, we wanted to insert between the successive contour lines, we want to insert one more. And so this is a hierarchical process until it allows you to insert one more interpolated line. So typically, by following this simple binary morphological interpolation equation, and we have converted this sparse contour data into dense contour data. I would say this is coarser resolution, this is a super resolution. So when we extend that to the grayscale case, you have two digital elevation models of two different time periods, and we want to slowly transform this into this one. So this source to target, and we don't have intermediary information. To simulate that intermediary information, and we hierarchically compute the morphological median computations between these two spatial functions. And then the equations are simply this. We take infima between I and j, suprema between I and j, suprema is eroded, infima is dilated, and once you get these outputs, and then you typically take the infima between those two outputs, you do that for all n values ranging between 0 to capital N, you get this median function. When you have source and median and target, between these two, source and median, you can compute one more median. Between median and the target, you can compute one more median. And this is a hierarchical process again. And these are some of the steps of the algorithm. And you can see this with some numbers we have given and given the results for, it's like a tutorial for someone to really understand. So this is source and target, the first level median. Second level medians are, it goes with a 2 power n fashion. And between this and this is computed. Between this median and the target, and this is computed. And this is a hierarchical process. And so we have generated a large number of interpolated functions in a sequence. And so these are animations which I could not show. And so this is from source to target, and so many interpolated images we have generated functions. And then this is with a flat structuring element. This is with a non-flat structuring element. There are certain advantages with flat and non-flat structuring elements. More details can be seen in these papers which are published in JSTARS and transactions of image processing. So these are some of the things. And then at the end, and I think I'm on time. And then with all these spatial algorithms, you have seen for retrieval, analysis, reasoning, modeling, and visualization. And so how to use them, and then can we really, if you take a specific dynamical system, I always say is a sand dune DEM. The dune DEMs will highly time varying. With time they actually change their superficial morphology. And can we really create a kind of attractor for the a specific geological or geomorphological system? What is attractor? A simple, I used to tell this example like a pendulum oscillating back and forth without any friction, and it goes back and forth, and its corresponding attractor is a kind of limit cycle, which is in a closed loop form. And the pendulum oscillating back and forth with a friction created, and it comes to rest state, and it loses its energy, and it comes to rest state. And its corresponding attractor is a kind of a spiral attracting to a central fixed point. So such kind of attractors can we really derive by, we have now very accurate data being acquired from with various different means, and we know the methods to retrieve, analyze, reason, and model and visualize. And if there is a way to really create some parameter based system specific attractors, and probably the predictability is has a way to really see it further. So this is what I mentioned. An open challenge is Earth superficial phenomena include numerous geomorphological features. Considering feature-specific attractors to better understand the dynamical behaviors of each and every geomorphological feature is a challenge. And mathematical morphology, a robust mathematical theory that Earth and planetary science communities need to pay more attention to deal with this type of challenge. Right? These are some of the books, and then I think most of the cases that I have shown, except a few, are there in this particular book of almost 10 years old. And other things are just like edited volumes. And then, yes, and with that, so there are YouTube lectures given in a NPTEL style. And so I can share those things, but they are all available on web. And so to understand the basics of morphological operations, how they can be implemented in a very tutorial style, they are presented here. And so with this, and I'm really grateful for my DL ship, distinguished lecturerships of both GRSS and Women in Engineering. And so thank you very much. And so any questions and answers, I would be very happy to answer. So probably I'll stop sharing so that if anybody wants to ask. question,
Yes.
and I can answer them.
Thank you, Dr. Dayas, sir, for sharing your valuable insight with us. Now
Yes.
it's time for us engaging in QA session. Participants, please feel free to ask questions. You can raise your hand. Yes. I think one of the participant named Sushant Pawar has asked one question in a chat box. Is there any
Yes.
qualitative and quantitative parameter to measure the performance of mathematical morphological operation as compared to the non-mathematical morphological operation? Also, its
Uh,
computational cost.
no, mathematical morphology is computationally expensive, but with all CUDA technology, it should not be a problem now. But non-mathematical validation, I don't understand. But most of the, if he is referring to the network that we have extracted from DEMs, and I would always say that as long as DEM is accurate enough, if there are no uncertainties, whatever the features that we retrieve are, very accurate enough. I'm not sure whether I have given him the proper answer. He can always counter me.
Yeah, yes, sir. So one more question from my side. So how DEM is different from digital surface model, that is DSM, and digital terrain model?
I would say terrain model is the moment you drape all terrain features, and that becomes a terrain model, and where you don't see actual elevations, and on elevations you see some terrain features, but that is not what we want. And typically the digital surface model is with a bare soil without any anthropogenic features, like buildings, roads, and all that. If you remove, and how that bare soil would look like with the elevation as the parameter, and that is the kind of the way the difference between digital surface model and digital terrain model. But if someone wants to do some kind of modeling, or geomorphic modeling or something, I don't think DTM will really be useful. DTM is a nice thing to visualize, to know where there are beautiful plantations and uh, urban features were there.
Okay, sir. Thank you. So one more question from Dr. Sangeeta Chaudhary, madam. Yes,
Yeah,
ma'am.
madam. Tell me.
Yeah. Hello, good evening, sir.
Yeah, good
Uh,
evening.
yeah, thank you, sir, for such an informative talk. So, I have one query. Like most of the time in image processing, people are using grayscale morphology, and the color morphology as well as three-dimensional morphology. That is very rarely people are using it. So, um, like
Ah,
in the
yeah.
perspective of remote sensing, how we can utilize this kind of morphology, and where exactly usage of this will be more effective.
No, just to give you list out some examples, like some cases, the entire mathematical morphology can be used in all hyperspectral image classification. If you look at those papers written by mostly this Bendixson, Jocelyn, and Brujon groups, and they have heavily used mathematical morphology with the name of morphological profiles. The granulometries that I have shown, they term it as a morphological profiles. Morphological profiles are nothing but granulometric analysis, and they have already been in use to uh, for hyperspectral image classification. That is one. And then this morphology is also highly useful for dimensionality reduction, band selections within hyperspectral image domain. And then 3D morphology, mostly to study the volumetric analysis. And so, if you are talking about a simple remote sensing, and yes, we know how a water body surface looks like, but is there a way that we can really quantify the volume of the water within that? I think by bringing both DEMs and then remotely sensed data and the 3D morphology, we can actually quantify the volumetric analysis of things. And so, but in medical imaging, yes, 3D morphology has gained a lot of popularity. Medical image analysis, and they do a lot of other CT 3D CTI angiography using mathematical morphology. They quantify many different parameters. There are, and so, but to tell you that graph morphology is a way forward, and the kind of erosion dilation that I have shown in simple binary and grayscale domains, now they are very nicely explained through graph notations. And then you can talk about any number of dimensions. It is not just 1, 3, and 4 dimensions.
Yeah, yeah. Thank you, sir. Thank you.
Yeah.
Sir, one more question? Can you hear me, sir?
Yeah. Tell me, Prakash. Yeah. Prakash, you are asking me something?
Yeah. Can you hear me? Hello.
Yes.
Yeah. So most of this morphological analysis.
It's very feeble, Prakash. I am
Your
unable
voice
to.
is not audible, sir.
Can you hear me now, sir?
Yes, sir,
Yeah.
yes.
Yeah, I can
Yeah.
hear.
So most of these morphological operations were kind of
Hmm.
performed to extract regular features like regular network features or regular, ridge network. But
Hmm.
what if we wanted to analyze destruction related works like earthquakes or things like that? Can we still use this method to do that?
So which one you said? Quake? No, you mentioned other than ridge networks, and can it be used for
Earthquake.
earthquakes? Yeah. So
Yes.
I think, see, with multiple DEMs and multiple data sets acquired at different time periods, and you can always see the differential morphology.
Okay.
At certain places there are changes. I'll call it as accretion. Other
Okay.
places there are also changes. Those changes are not accretion but erosion. And there are places there is no change at all.
Okay. Okay.
See, accretion and erosion, and then places where there are no changes. And
Yes.
if you can really figure out where there are accretions, where there are erosions, and where there are no changes, obviously these are the regions one has to pay attention. And but using morphology and then interferometric studies, I would say, using morphology somebody has done, but which has not gained any attention. Morphological phase unwrapping to find out the fringe lines where there are drift changes in the fault lines. And if you look at Howard Jepker's work in Landers earthquake, after Landers earthquake, a particular fault was shifted for about 15 centimeters, which you could really quantify through interferometric analysis. But that interferometry now people can really do it with mathematical morphology. That's what I'm saying, morphological phase unwrapping, and which has not gained any attention. And it was there at one corner, somebody has published it. But when we tried and we didn't get proper result. But to tell you that, mathematical morphology is very popular in signal processing. And so seismographic analysis, seismological signals. And if someone wants to get into earthquake related studies, and at least, and I can suggest signals, signal analysis is very popular in seismography studies, seismology.
Yeah. Okay, sir. Thank you, sir.
Yeah,
Yeah.
yeah.
Yes. Thank you, sir. Now it's time to express our sincere thanks to our eminent expert, Dr. Daya sir, for his insightful presentation on mathematical morphology and understanding spatial data like digital elevation model Also, morphological interpolation and various mathematical expressions were explained nicely, sir.
Yeah.
Sir, we're truly grateful for your time and expertise that you shared with us. Your session has given us a lot to think about various aspects and the various applications in this area. Yeah, thank you once again.
Thank you, madam. Thank you so much. Yeah.
Thank you so much.
Thank you so much. Yes. It was a pleasure talking to you people. Yeah.
Thank you so much.
Yeah.
Yeah. Thank you, sir. Yeah.
Thank you, Prakash, and we'll see a way to meet sometime. Hmm?
Yes,
Yeah.
sir.
Thank
Bye.
you so much, sir.
Thank you, madam. Sangeeta, madam. Yeah. Nice. Yeah. I'll close it. Thank you. Thank you, Deepthi. Yeah.
Thank you, sir.
Thank you. Bye.
Prakash sir, yes, we'll have a break of 5 minutes now.
Uh, okay, ma'am. Sure, sure. Kuldeep also will join. I'll get in touch with him. Yeah.
Okay, okay, sir. So participants, you can take a break of 5 minutes. Please join soon. Prakash sir has joined.
Sir is not available in meeting.
Yeah. He's trying to join.
Okay.
He's joining it. Yeah.
Okay, okay, sir.
1 minute. Yeah.
Good evening, sir.
Hello.
Yeah. Hello, sir.
Hello, sir. Good evening.
Hello, Kuldeep.
Hi. Hello. Am I audible?
Yeah, you are audible, sir.
Okay. Uh,
Shall we start, sir?
yeah, sure, sure.
Sir, you need to check screen sharing and all.
Yeah, let me. Yeah, that's what I was doing. Let me. Okay. Are you able to see the screen in presentation mode?
Yes, sir. Yes.
Yes, yes.
Just
Okay.
slide once. Yeah,
It's
fine.
proceeding, right? Okay.
Yeah.
Okay. Nice. Yeah, we can. Yeah, we can start.
Yeah. Good evening, sir. Welcome to our FDP, ATAL FDP, sponsored by AICT. And yeah, so Kuldeep sir is currently working as a research scientist at Reliance New Solar Energy at Reliance Industry Limited. Before joining Reliance, he was a research scientist in the Computational Urban Science Group, CUSG, which was a part of the Computational Science and Engineering Division at Oak Ridge National Laboratory, USA. He completed his PhD in spatial image information mining from the Indian Institute of Technology, Bombay, India in 2017. Later in January 2018, he joined Oak Ridge National Laboratory as a postdoctoral research in the Scalable Geo-Computational Group. During his research career so far, he has performed applied AI and computing research to address various urban-centric problems. His experience and interest in AI/ML range from knowledge, presentation and reasoning, reinforcement learning, deep learning, and geosemantics. Kuldeep has experience and interest in utilizing various HPC platforms such as GPUs to solve developing a scalable end-to-end human settlement detections, overflow from satellite data, and its deployment on a Titan supercomputer ranked 1 in 2013. From the application side, he is interested in research related to disaster situational awareness, decarbonizations, and energy optimization. As a research scientist at CUSG, he explored more urban applications such as transportations and building energy. Kuldeep is an active member of professional societies such as ACM and IEEE. Kuldeep has served as a referee for several international journals that includes the IEEE, JSTARS, TGRS, GRSL, and several others. domain of geoscience and remote sensing. Energy and applied energy from domain of energy, uh, concurrency and computation, practice and experiences, and journal of supercomputing from the area of high performance computing HPC. He has served as a referee and a programming committee member for several workshops and conferences such as ACM, SIG Spatial, IEEE Geoscience and Remote Sensing Symposium, IEEE Big Data, and Earth Vision CVPR workshop. So, sir, it's a great honor to have you here, such an eminent personality with us. A warm welcome to you, sir. Yeah. So today, sir is going to talk on a Geo HPC. So now I request Dr. Kuldeep, sir, to hand over the session. Over to you, sir.
Yeah.
Thank you.
Yeah. Thank you so much, Ashwini ji, for that warm welcome. It's really a very good feeling to share the some of the work that I have done, knowledge with you all, and we will try to keep the uh, session more interactive. I'll try to make it more interactive through questions, and so please try to interrupt me in between. I have prepared couple of slides, but we will uh, within a given time limit we'll try to see how much we can cover, and assuming the question answers and all. So no need to postpone your questions towards the end. I think we can keep it more, interactive. So please feel free to, interrupt me. So, okay. So now GeoHPC. So basically, GeoHPC is very vast area, and I think I haven't given any specific topic prior to this session, as on what particular topic I will speak during this talk. So basically, so this is the topic that I'm going to present. I'm going to discuss with you today. So it is on scalable object detection workflow for remote sensing data. What are the challenges, performance analysis, and deployment? So I'm currently working as a research scientist in Reliance Industries Limited, and the work that I'm going to discuss with you today was done when I was at Oak Ridge National Lab. So it is slightly older work, but the concept and the the fundamentals will remain same, and we can apply today also. So on the right side, I'm showing my name of the colleagues who contributed to this work from Oak Ridge National Lab. Okay. Uh, now, so since we are talking about geo-HPC, meaning we are concerned about geospatial big data. So before diving into the actual topic, I thought let us discuss something about the fundamentals. So basically, geospatial big data. Why do we need high performance computing platform? So we are thinking about geospatial big data, or the big data in the context of geospatial. So when can we say that a data is a geospatial data? So meaning it is a specific type of a big data or data that contains location information. I think we all can agree, and I think you have been listening to some other talks also. I have seen the topics, so I think they those talks also discussed about geospatial, high performance computing, semantics, and so on. So by now, I think you have got. I assume that you have got a very nice understanding of how this geospatial data is different than your conventional data, which is non-geospatial in nature. So we have the location information, correct? And here on the left side, I have listed.
Key Kawali.
Yes.
Oh, thank you.
Oh,
Okay,
Hello.
okay.
okay. Okay.
Intelligence.
Okay. I think someone's mic was on. That's fine. Okay. So what I was telling, that on the left side, I am showing you some of the major sources of geospatial information. So one is the Earth observation data. So typically, remote sensing satellites captures these, images, multispectral images, through different sensors. So that's how you capture this Earth observation data. Uh, just to give you an idea about the volume of the data. So NASA, in one of the reports that I recently searched, I found that NASA's Earth observation data, the data that NASA's satellite capture, will grow up to 250 petabytes by 2025. So this is only the remote sensing imagery data. But other than those data, NASA also captures different Earth observation related information through sensors and all. So that will be, you can understand the amount of data that we have, at least from this remote sensing imagery or the platforms. Then the second type of sources of the data, which has location information, is generated through geoscience and model simulations. So basically, if you have heard about climate model simulations, the models that basically simulate the climate condition or the weather, not the near time, but for the next 10 years or 20 years of horizon. So those are the models. Basically, they crunch a lot of, process a lot of data, and they generate a lot of geospatial data. So the sixth IPCC report, Intergovernmental Panel for Climate Change Committee, basically the next sixth report has estimated to produce over 100 petabytes of climate model simulation data. So once they produce the data, they basically do some calibration, and then it tends to produce even more data. So that is the another source of data where you see geospatial, the big data which is geospatial in nature. Then all of you know about Internet of Things. Nowadays we are surrounded from these low cost sensors which are connected to internet. So by 2024, means by the end of the 2024, which is I think December, in this month, it was expected that the total number of IoT sensors will reach around 18.88 billion. So those many IoT devices are there, surrounding us. So you can, and those IoT devices ranges from variety of types, right from our mobile device, then the agriculture related sensors and so on. So again, they are generating a lot of data. And then another category is the volunteered geographic information. For example, when you do some tweets or Facebook tweets or something like that, then you tend to generate some information, and you're volunteering to their repository, to their database. And if you put your geolocation, that information is called as a geographic information, right? So approximately 24 millions of geotag tweets are generated each day. So that is and these tweets are loosely, we can call it as a unstructured data, because you tend to mix the text data along with the image and so on. Then you have the location information. So this is just to give a glimpse of why this HPC, high performance computing, is very important in the context of geospatial data. Correct? So I hope that is correct. If are there any doubts or anything, or someone wants to share something in this context, some new information, please feel free to jump in. Okay. So now we know that we are surrounded by volume of data which is geospatial in nature. Okay. So now coming towards, in this particular presentation or the talk, I'll be mostly dealing with the Earth observation data, specifically the satellite image data, the multispectral image data that is being captured by satellites, different satellites and sensors. And the specific topic, if you would like to know, is so it's a performance analysis and optimization for scalable deployment of deep learning models for country scale settlement mapping on Titan supercomputer. So this was the work that I have done when I was in Oak Ridge National Lab. And as you can guess, the application of this work was country scale settlement mapping, which means for a given country, it's not that we want to find out the settlement, or the area where the settlement can be there. For example, buildings, or the malls, or those kind of other structures where settlement basically can be present. So those kind of artifacts or the structures we want to find from the remote sensing image, high resolution remote sensing image, but we want to do at the country scale. It's not like it was not for the small region, but for the entire country. And this particular problem statement was very good example of why we need high performance computing type of system to deal with this type of problems. So today I'm going to discuss this specific problem with you, and what were the various challenges that we faced, and then how we basically try to dealt those problems. So just to give you all some motivation. So basically, this project was funded by Gates Foundation, Bill Gates and Melinda Gates Foundation. So this was a problem statement that was given to us. So if a government organization wants an approximate count of a vaccine, of a particular vaccine X for some country Y, where the updated population or the census data is not available. So suppose that particular company or the vaccine manufacturing company wants to ship that data, wants to ship the vaccine to that particular country. So before shipping that, we need to know the total count or the total population information, right? But what if that country does not have the updated census data? So now in our country, we have the regular updated census information available, but there are countries, for example, in the Africa continent, there are few countries where you don't have, specific updated census information. Then how to do that? Okay, so that was the problem statement. So basically, since we come from geospatial background, so the one thing that come to our mind is we can use high resolution remote sensing image of that particular country to map the human settlement. So at least from the uh, earth earth observation image, we can at least try to mark the pixels on the image, remote sensing image, that are sort of that looks like a settlement. Okay, that we can do at least. And then on top of that, that particular information can be uh, provided or can be input to the population distribution model. So there are different statistical models which basically take several other inputs along with the this type of information, where you have the satellite image, and then these are the greenish yellowish pixels which are marked as a settlement. So basically, this type of information can be provided as an input to the population distribution models, and that those type of statistical model will give you the estimate of the population of that particular area or the country or the region. So our problem scope of the problem is this, that you have the input satellite image, high resolution image, and you want to identify those pixel or mark out those pixel which seems to be settlement or seems to have human settlement present. So that was the problem statement. So is that the problem statement clear? The is the motivation clear basically?
Yes, sir.
Okay. Yeah.
Sir,
Yeah.
sir, can I ask?
Sure.
Hello?
Sure. Yeah. Yeah. Yeah.
Sir, the motivation is clear to me, but I only wanted to know that we are not having the census data. So from this image, we will just get where the settlements are. We will not get the
Mm,
actual population.
correct. Correct. That's true.
Uh,
Yeah.
so then how are we going to use it for further work?
So basically, uh, for census, we need to do survey. That is altogether different issue. But suppose we don't
Okay,
have that mechanism in a particular country. Suppose that mechanism is not present. But what is the
okay,
best input that we can have is the satellite image. Suppose this type of information is available, satellite image.
okay,
Then
okay,
at least we can try to mark the settlement pixel, right? Settlement
okay,
pixel.
yeah, yeah,
And
yeah,
with some assumption, for example, if a settlement if of size this much, say for example, if it
oh,
is covering say 20 meter by 20 meter ka area, then
okay,
you can have some safe assumption that it might have say 10 people, or it might
okay,
something like that, and those kind of
okay,
assumptions are made in these population distribution models, which
okay.
will take this type of information as input, and then it will estimate the population or the number of people in that manner
Oh,
as output.
okay.
Yeah. The
Okay.
scope of the,
Yeah.
so the scope of the work is your input is satellite image, your output should be the
Uh-huh.
marked pixel where the settlement could be present.
Okay. Okay. Yeah. Thank you, sir.
Yeah. Yeah.
Yeah.
Okay. Yeah. Nice. All right. So now I'll quickly touch upon the some of the aspects that I feel uh, contributes to this type of work. Meaning nowadays we know that many satellite platforms are available. It is many Indian remote sensing satellites also produce high resolution data, high spatial resolution data. Meaning one pixel is covering almost less than 100 centimeter of the space on the Earth from that perspective. And then spectral resolution is something like in what wavelength you can capture the information that is being reflected from the Earth. And again, we have the lot of improvements in terms of electronics, sensor electronics. That's why we are able to get the images with the improved satellite as a spectral information and increase the revisit period in how much time, how frequently satellite can revisit the same area while revolving the earth around the earth. So these are also the factors which contributes, this particular thing. This contributes the increased earth observation data. So the advancement in the sensor technology that we are seeing today, as well as the increased advancement in the satellite technology basically. So this again, these new opportunities, this provides more opportunities to us to understand more about the Earth at a finer spatial scale. But since the spatial scale is also increasing, that means you need to process more amount of data. So that's the balance, or that's the challenge that we need to meet. That's what I'm saying here. So basically, mapping human settlement at a country scale from a high resolution satellite imagery is a challenging task because we need to process billions of pixels in a reasonable time, of course. And suppose there is some time critical event, for example, your application, or your requirement is related to, say, disaster. Suppose there is some flood or something happened, or earthquake happened, and now you want to process the image and try to understand the disaster affected areas. So those are the time critical events. So in those particular for those particular applications, we need to, the situation becomes more uh, difficult, and the application of HPC become more prominent in those kind of cases. So in our context, we used supercomputing facility. It is a type of high performance computing system, but it's at very big scale. I'll show you the nature of the supercomputing facility in the next subsequent slide. But before that, let me tell you the object detection. So we call it as a scalable object detection workflow because it's an end-to-end workflow. It includes the training, and then further, once the model is trained, then you need to deploy that model onto the system to process the satellite image and those type of things. So it's an end-to-end workflow. So we developed this end-to-end deep learning based human settlement mapping workflow, and these four are the major characteristics of that workflow. So it's a scalable meaning uh, it you can use the same workflow for one country, for another country, because irrespective of the area of the country or the size of the country, um, our workflow, we try to make the workflow fault tolerant. So we'll discuss about this fault tolerant more in this presentation, because that is the core of the today's session. So by meaning of fault tolerant means we want to, so when we run some job, some big task at in high performance computing environment, especially when that HPC system is shared among multiple users, there might be some situations where that system might fail, or something might happen because of your job might get terminated. There could be some known reason or unknown reasons also. So now, suppose you have your processing is finished, 90% finished, and if your job is being terminated because of any reason, so when you again restart, or what will you do? Either you can resubmit the job onto the HPC system, uh, or what you can do is, but if you want to resubmit the job and start from the beginning, that means the earlier results that was processed, or earlier work that machine has done was wasted basically. So we want to take care of those situations. So by meaning taking care of this type of failure, and making our system sustainable, is called as a fault tolerant system. And then those system mostly now come up with the GPU resources, GPU cards basically. So we need to also understand, we need to make optimal resource utilizations, whether it is GPU, whether it is CPU or the RAM. We need to understand that those processing are sometimes costly in terms of money basically. So if you are running your job for 1 hour, that HPC facility or the organization which hosts that HPC facility will charge some amount to your project, or we need to pay. So there is some monetary aspect involved. And then we also deployed this end-to-end workflow on the Titan supercomputer. So those are the four important things that I want to highlight. Specifically, I will be talking about this fault tolerant, how we made that workflow fault tolerant basically. So now, since I mentioned about this Titan supercomputer, so let me give you some glimpse of it. So this Titan supercomputer was established in was commissioned in 2011 or 2012 basically, and it was there until August 2019. So, and after that it was decommissioned. They just removed the entire system. So basically this is the pictorial view of the Titan supercomputer, how a particular supercomputer looks like. So it has in a summarized fashion, if I want to describe, it has multiple cabinets. Each cabinets have multiple nodes, and each node has a dedicated CPU and one dedicated GPU. Okay, so like our cupboard basically, right? Or the wardrobe. So we have these cabinets, and then we have nodes. So each node is look like it's our CPU basically, computer CPU, but it is stacked horizontally, one after the other, one below the other. So likewise, the cabinets that you are seeing here, so we have around 200 cabinets in this system, and each cabinet and then total number of nodes, if you want to calculate, those were 18,688 nodes. Those many uh, uh, racks were there. One node is one rack. And then how many CPU cores per node is 16, and there was one GPU per node. So that means we have around 18K GPU system or the GPU cards in total Titan computer. And then there are some other specification. So if you collect all the CPU cores, total number of CPU cores, so those many close to 300,000 CPU cores were there in the Titan supercomputer. So that was the scale of that facility, and hence this facility was shared among multiple users, multiple universities. People can have account there, and based on the usage of that system, those users will be charged uh, based on whatever contract they have. So that is one example of the supercomputer. So now this supercomputer was already decommissioned when I was there, and then there are two more supercomputers that they procured. One was called as Summit supercomputer, and then there is current supercomputer which is called as Frontier. So online you can check, you will get an idea of the scale of the supercomputer and different specifications. Meaning after Titan, how the technology has evolved and what type of CPU and GPU they used. Just for our understanding or the visualization of that scale. So we had the project that we had. Through that project, we were able to we were allocated some core hours basically, and then we used those core hours. Core hours meaning how many hours of CPU cores of processing that you can do on this supercomputing system. So, and based on that, our project was charged that much amount of bill uh, at the end of the year. So that was the system. Okay, so now this was about the specification and how it looks like. But in any high performance computing system, if you take any example, then how we typically tend to submit the job or submit or do some processing. So this is just to give one particular illustration. So typically user will, there are some dedicated nodes in a HPC system which are called as a login node. So user typically tend to log in and through this node. And then once you are into the system through the login node, you will prepare a job submission script. So in every HPC system, there are some standard templates that we need to use, and through those template, you will provide the exe file or the Python file, whichever, whatever you want to run onto these nodes to execute your job. So you will create that job submission script, and you will submit that job submission script to the scheduler. So there is a component called scheduler. So scheduler basically uses different, scheduling policies like first in, first out, last in, first out, those kind of thing. There are a lot of advanced policies are available, but you get the idea. So it's a queue system basically it maintains, and then these job scripts are put it into the queue, and then once particular jobs number has come, it will be assigned to one particular node, whichever is available, and then that node will basically run the job. Output is written. So on the right side, it is just the illustration of how different jobs can be overlapped. Suppose there are 6 nodes, and then various jobs, suppose 9 to 10 jobs, then how these jobs can run parallelly, basically. And this, it is not required that all the jobs belong to same project or same user. It can be from different user also. So now, towards the end of this session, when I'll show you some of the results, you will see this type of chart also, where we try to simulate this type of job submission for this settlement mapping workflow. Okay, so that was about the how a typical HPC system looks like, and how we typically perform job scheduling on this HPC systems. So is there any specific doubt or anything that someone wants to discuss?
So can I ask?
Yeah, sure.
Sir, I just wanted to know what tools you had used to process this job scheduling and all, apart from the
So
tools that you require for implementation of spatial work.
hmm, yeah. So this is purely from the HPC side. So typically, if you see the open source tools, Slurm is a tool which is basically used to um, uh, use as a job scheduler for any typical HPC system. It's an open source
Hmm.
tool. But
Okay.
these large companies, say for example IBM or any big companies which set up this type of big system, they basically have their own scheduler. So it is built on the Slurm scheduler only, but they have their own recipes or they have their own. They make it more customized based on the user requirement. Uh, Customized in the sense of the job scheduling policy. They might not use simple first in first out kind of approach, so they have made some customization. So based on which company that particular HP system is maintaining, you will have those kind of schedulers.
Okay. Okay. Thank you
Yeah.
so much.
Okay, so I think what I tried to cover so far was what was the problem, uh, what was the problem, what do we mean by high geospatial big data, and then what problem in that entire geospatial big data sphere, what specific problem that I'm going to discuss, what specific problem we tried to solve, and what particular computing environment that we used, which is supercomputing environment, and what was the characteristics, some of the major characteristics of this object detection workflow. So now, before moving forward, I would like to take a pause here and explain you uh, different challenges that we faced. So it was, for me, it was the first time when I was using this type of big system, and through my experience of initial days of using that Titan supercomputer, those and specific to our problem, I found these specific challenges that we wanted to overcome, or rather we wanted to address for the settlement mapping. So first one is preventing data loss due to runtime failure. So I briefly touched upon this particular component, that during runtime your job might fail, right? So you need to make sure that your job, because whatever data that is being produced after processing the your input information or the input image, you need to preserve that somewhere. Either you need to store it or do it somewhere. But if you don't do it, then that information will be lost in the case of failures. Then second point is very important point is resource utilization, proper resource utilization, and avoiding long tail effect. So here basically I'm showing one particular example, and this graph, if you see, it has a long tail. What do we mean by long tail? For example, let's say there are five processes or five nodes that you have reserved for your job, okay? And you have distributed your inputs among these five nodes. Out of that, four nodes finished its processing within 1 hour. 1 hour, four nodes or four processes has finished their performance. Now only one node or the process, the remaining fifth process, it kept running for say 2 hours. But since you have submitted only one job, and through that job you basically reserved four nodes or the four created four processes to process your information, that entire the earlier four processes or the four nodes were still stuck with your job, right? And those resources cannot be used for to solve any other problems or to be allocated for any other different jobs. So those four resources were basically you lost because of the poor resource utilization. Those four resources or the 1 hour of time was basically lost. So that is one simple example. And when you have that type of job scheduling or maybe allocation of your resources for your job, then this type of situation will arise where uh, most of the node will finish early, but some of the nodes in your job will keep executing the process for some prolonged amount of time, and that's how you tend to um keep those remaining or the processes which finished earlier, they remain idle. They cannot be used for any other jobs. So that was what I meant by resource utilization. And then third point was constraint posed by Titan's job scheduling policy. So basically, this is very much specific to the Titan supercomputer, and maybe some other HPC system or any other system may have some scheduling policy. So I'll give you one example later what this job scheduling policy looks like. Okay, so let's hold on this particular point, and we can come back to this. And then the last point was tuning to old K20. So basically, when this Titan supercomputer was manufactured or when they were set up, um, the latest GPU was K20, NVIDIA Tesla K20 GPU. When I joined ORNL, that time NVIDIA K40 GPU was there, was the latest GPU. So this K20 GPU was the old GPU, meaning it has less number of cores, lower small size of RAM. But by the time when we started working on deep learning application and all, um, which is actually large amount of data, so we need to make sure that, and this GPU, initial GPUs tend to have small RAMs, so SRAM basically. So we need to make sure that when we assign job to this one particular GPU, when we put your image onto the GPU, we need to make sure that that entire image or the data will fit into the GPU, into the GPU memory. So those were the some of the challenges. But nowadays, I think if we have decent size of GPU, or even if we don't have decent size of GPU, then we need to make sure that, or rather, we need to fine tune our code or the scheduling such that it will make good use of whatever GPU resources we have. So that was the intent. So are these challenges clear? Meaning the most important is this resource utilization, and the first one basically runtime failures. So runtime failures is sort of, I think, we expect, we know, we can visualize. But let me know if you have any doubt regarding the second uh, point, which is about resource utilization and this long tail effect. We will come back to this third point, and also this most of these points again in some form in further in the presentation. Okay, so these were the challenges which I felt were necessary to address when we deploy this settlement mapping workflow on Titan supercomputer. Yeah, this is how the very broad overview of how the settlement workflow or object detection workflow looks like. It's very generic actually, meaning you see that there are like broadly there are four stages. One is image acquisition, second one is processing of the image, then third one is model training, and the fourth one is once the model is trained, you need to deploy the model. So there are, I think this is the common steps that we typically follow. There are two things specifically that I would like to, two or three things specifically that I would like to highlight. One is the image acquisition. So we have given a specific block for image acquisition because when we saw this big supercomputing system, most of this system, broadly this system or the nodes in the system are divided into three parts broadly. One, one set of nodes are called as a computing nodes. They have only the computing power. Okay, they cannot store the data. They don't have the hard disk kind of permanent storage. But there are some other nodes like this. For example, these are the storage where the data can be stored. And then, for example, there is one specific file system called Luster file system, which is specifically the high performance, which was meant for high performance system like this. So there are some many other file systems that are available. So those type of file systems were being used in the storage to store the data. And then one type of node which I already mentioned called as a login node. So broadly, you will see this type of division. So now image acquisition was separate because you need to, first of all, you need to have data into this storage. And then from the compute node where your deep learning model is running, you need to fetch your images during runtime from the storage server to the from the storage node to the compute node. So the important point is there is a time. It's not that we have data available in your node. So there are various strategies to. So there is a time loss between the transfer of the data. So what point I want to make is you need to have optimal, overlapping of the job. Suppose you're loading your deep learning model into the node, but before loading, you try to make sure that your image has already fetched into the node in a particular compute node, and then it is available into them. So those kind of consideration must be made. Um, uh, Generally, we haven't done it at that particular level, but I think this is very important point that I wanted to make. Then image processing. So basically, why this important, because so the geospatial images basically they tend to come, or the remote sensing images, they were of very big size. A typical, just to give you an example, the images that I dealt with had close to 40,000 cross 40,000 number of pixels. That is the size of the image, 40,000 of rows and 40,000 of column, for example, of that order. And as I said that the GPU or the most of the time those are of memory. So it is difficult to put that much amount of data at once into the GPU or sometimes into the RAM of the node. So you need to have some kind of, say, chopping of the information, tiling of these big images into the small chunks, which you can process efficiently, which you can basically put it onto your GPUs, so that GPU memory can be efficiently utilized. So that type of mechanism has to be there. Now, for different type of geospatial data, this image processing or geospatial processing will be different. In our context, it was mostly tiling and then some other geospatial operations that we did. And development. So basically, this is very common nowadays. We all know how we train the model. We need to have the label data. We train the model and so on. That is very much well understood. And now once we have the model, you deploy not only one model. Suppose you have say hundreds of images that you want to process. You deploy 100 instances of that one trained model on 100 different nodes, and then you provide images in parallel batches to all those 100 nodes so that they can be processed in parallel. So that is one important thing. You are going to parallelly you will generate those many instances and then you will execute. So other than these 2 3 points, I think the entire workflow is very much generic, and we can you can actually visualize this particular workflow. Okay. Um, hmm. So basically, I will focus more phase, those kind of not new, but people were still exploring, and that field was still growing. So this was very simple convolution neural network based architecture that we used for the settlement detection. Nowadays we have very much deep architectures like ResNet and so on. Now transformers are there. But that time when we started with the simple convolution neural network architecture. And here if you see one input image that you process in your convolution in your neural network was of size 140 cross 144 cross 144, and the amount of data or the size of the actual remote sensing image, one particular image covering some area of that particular country, was in the order of 40,000 cross 40,000 pixels. So that's where this image processing block came into picture, where we basically tiled the information into this type of chunks. Okay, so now once the model is trained, you go to the fourth phase. Uh, but before that, I'll just briefly tell you about the platform that we used to train this deep learning model. So there is something called as a NVIDIA DGX box. Uh, the typical this DGX box looks like this on the right side. If you see, it's mostly a CPU, but architecture-wise, it is like it has two CPU. Uh, two CPU processors, and then there are total eight number of GPUs. Uh, a set of four GPUs on the left side. Basically, you will see here they are interconnected through each other, and then another set of four CPUs are here. So you can loosely say that this CPU has close connection with these four GPUs. CPU one has close connection with these four GPUs. So now actually these eight GPUs are connected with each other through a very fast link for the data transfer, which is called NVLink. So this type of DGX box actually very useful when you do model training, especially large model training in parallel. So for example, suppose you have ResNet 50, ResNet 150 model, or maybe transformer for that matter. You cannot just work on one GPU. If you want to do training much faster, this training is intelligently distributed among multiple GPUs. So the weights are shared. Sometimes training data is shared, and then at the end of the training, the loss will be averaged, and those kind of strategies are there. But the point is, you can do a parallel training. You can train your model parallelly among GPU. So for our task, we had that particular resource available. So the model was trained on this. So I wanted to give a quick information on the training platform. So basically, the training platform was the DGX box, which was the state-of-the-art deep learning training machine that was available. But the deployment platform was different. So that was the difference. So this GPU was Tesla V100, which was the cutting edge GPU that we had that time. But the deployment platform, which is Titan supercomputer, had K20, NVIDIA's K20 GPUs, which were very older GPUs. So there are a lot of differences in terms of number of cores, number of memories, and so on. So uh, architecturally or the workflow wise also, these are the two differences that we had. Okay, so I'll quickly go through this flow it's not like very informative, but it will give you some idea of, in terms of how we are doing it. So basically, in center you can see that there are three phases. There are three steps. One is building the model or invoking your trained model. Um, and this is in the context of model execution or the inference, the phase number 4 basically, where your model is already trained and now you want to deploy that trained model or the multiple instances of that trained model among different multiple nodes. So what could be the general, uh, flow or the processes that you follow? So first one is you need to first invoke the model basically. So here we are calling it as a building model. So please don't go to the specific wording that I have used. But in general, typically, when you have trained model, invoking your model means you will those trained weights are also stored into the file system, storage file system. You need to first invoke, read those weights, then build a blank model basically of your model structure, then initialize the weights using the trained weight. So that was the broadly that is the process that is being happening here. And then once the model is trained, basically then you will invoke the prediction block. So prediction or inference, whatever you want to call, and it briefly involves this. So you read the image, you perform the image tiling. As I told you that the GPU had the limit of its RAM basically, right? It has lower RAM, so we could not process the entire satellite image of 40,000 K cross 40,000 size. So that was the limit. So we had to do tiling, and once you have performed the tiling, then you will create the batches of those image tiles so that you can send one batch at a time to the GPU, from CPU to GPU, and then GPU will basically process your images. Typically, this is being nowadays it is being done. Um, these type of details nowadays are hidden from the developer, but that time when we code this particular workflow, we had to manually tile the image, batch it, meaning once you once you made the tile of 140 cross 140, then you need to physically stack all those 140 cross 140 one after the other and make batches of those stacked small size images. So that uh, at that level we had to do the coding. Nowadays it is being done automatically. You just need to provide the batch size, so 64 or 32, so on. So we had to do it, and then we need to send that information to the GPU exclusively, and then invoke the GPU inferencing. So nowadays, again, these processes are also being done very. If you do model.predict, for example, then it will automatically select the GPU and it will perform the inferences. It will transfer the data through the batches and it will perform the inferencing. But that time we had to do it at this level. And you will repeat this process until you have finished or exhausted all the batches that you created. And once it is there, you will so the output of this is settlement map. You need to find out what are the pixels into the input image that you send to the GPU, were contributing or were classified as a settlement pixel. So then that output patch or the array, you need to basically take it to the CPU and then fill that big 40,000 cross 40,000 ka blank array to the by using this output, output mask. And at the end of this, basically, you need to write this classification map, so to say, to the file system, the storage system, which is the persistent storage system, basically, so that the data can be then further used. So that is the broad, end-to-end view of this model execution of the inference pipe phase. So I'll take a pause here, basically. So what I present discussed so far was the what were the different challenges that I thought were important when we try to do this task on Titan supercomputer. Then what were the challenges, and then what was the how the workflow looks like, and what were the different systems that we used. and the broad overview of the how the inference pipeline look like when you want to deploy this trained model onto Titan supercomputer, how it is look like. So till now, I'm still setting up the platform, but please let me know if there are any doubts or any thoughts or something like that. Especially, uh, I think this resource utilization and long tail effect is very important. Is very important when we work on this shared resources or shared computing resources facilities. So that was the main, heart of our problem which we tried to solve. Okay, so I assume that I think it is uh, we are all okay with uh, this workflow. Now, let me jump to the more specific, topic or the concept. It's a load balancing strategy. Uh, so please try to remember the resource utilization and that long tail effect point and what the meaning of it. Uh, so it will be whatever we are going to discuss now will be related to that only, and how we basically try to optimize the workflow to address that second challenge. So now load balancing strategy. Some of you might have heard about it. Some of you here and there we have heard about it because our CPU mostly does load balancing internally at operating system level. But here we are trying to, balance the computational load in such a way that we try to address some of the points or the challenges that we discussed earlier. So here some of the statistics related to the data. So here the load is actually the data load or the computation load that I'm referring to. So you know that we are using this remote sensing imagery. The country is the country called Republic of Zambia. It's a African country. The data that we had was captured by Worldview 3 satellite. At that time, the country Zambia area was somewhere around close to 700,000 kilometers square. Um, and the geotiff or the remote sensing image that we had or the data that we had consisted of uh, close to 5,400 or 5,500 images. So total size was 13 TB. And here I am plotting or I'm showing you the distribution of the image size. So this is just in GB. Most of the image size they were in GB or more than 1 GB or 2 GB. Um, Here, if you see, although most of the images lie somewhere here, but there were some images uh, which were of small size compared to the entire. These are the outliers typically, which I want to highlight. And there were some outliers or the images whose size were actually very high. You can see that. So this discrepancy or the the variation in the size might be common or might be very specific to your application. So it is based on the data that you got from the data company or the data producing company. So this could be because the number of rows and number of columns in your image might be different. It might cover small area. One image might cover big area because there the coverage was higher, satellite coverage was higher. Because of any reason, this kind of variation may occur. Correct. So the point, if you have guessed already, the point that I tried to make here is the data or the workload might be of different size. Um, so what? Okay. So even if we have this imbalanced workload, then what was the problem basically? So now the problem is again there is another visualization. Uh, So here I'm showing same information, same meaning the data is same, but here I'm plotting number of rows versus number of columns. So if you see that most of the images had the number of columns into the image within the range of say 35,000, 33,000 to somewhere around say 44,000. If you consider these images, and so this is the scatter plot of those values for each image. So for each image, if you count number of rows, number of columns, and you plot it here, it will look like this. And but if you see that number of rows has variation, so there is a lot of variation into the number of rows. And we tried to come up with some groupings of it. So one policy to partition this workload was just to do some grouping based on something, some clustering mechanism or very simple rule based or any mechanism you can use. But the idea is you need to basically generate a sub partition of your data. So the question that I posed was, what will happen if we have this imbalanced workload? So now assume that you use all those 5426 images and assign and create only one job where you will allocate almost 5426 node onto the Titan supercomputer, and all those nodes, 5000 nodes, were allocated or assigned only for one job. So in one job, basically you will have some processes assigned to some of the nodes, which will process the small size images. Majority of the processes and the nodes will basically process these images which are somewhere here. And there are few nodes or the few processes will get these large size images. So now I hope you are able to see the challenge. So what will happen? Most of the processes, some of these small size images will finish their job first. Most of the processes will finish their job somewhere in the meantime. And these processes, some of the few processes which got this large size image will take more time to basically process the information. So now the problem is, since you have executed one job for these this small amount of large images, once we need to all the other processes need to be almost 90% of the computes or the nodes need to wait, and those compute cannot be or those compute nodes cannot be reassigned to execute any other job which is in the queue. So that is a wastage of the resources. So that was the point that I wanted to make here. Is that intention or the motivation clear, or any other thought or idea? Or any other thing? This was very basic thing that I tried, but you might have used some advanced approaches that can be used. Please feel free to jump in. And actually, this is something I don't exactly recall, but if you see the operating system 101, the basic book that we typically refer, there we might see similar kind of load balancing strategies with some variation, of course. This is the most basic that I thought might be useful as very naive strategy. Okay, so I think the problem is clear, that you don't want to assign all these images or the processing of all these images into one job. So then what will you do? As I shown you, you tend to split your data or the information or images into different partitions based on any rule. You can have some complex rule which is based on the size of the image storage, or maybe based on say very simple something similar to say number of rows and number of columns, some rule. So here I came up with some strategy and tried to group those images into different clusters. So intention was, instead of assigning all these images as a one single job, now you have 6 different jobs. And maybe what will happen, say for example, job 0 is might be very much it consists of images which are of small sizes. So you can group all the small size image into one particular job and allocate that job one particular set of nodes, which is independent from job 1, for example. So each of these jobs are independent. So whichever job finishes first, those compute node can be released after writing the output, and that can be used. So that way we are trying to introduce the resource utilization. So that is the fact. That was the main motivation, and this is how we tried to address this problem. But as I said, this is very nice strategy. We can use any other strategy also.
Hello.
Uh,
Uh,
yeah.
Sir, can we do rescaling or resizing of the images based on their job? So it's good to analyze further after the
Uh,
after.
you mean to say instead of that is good strategy, no doubt about it. But your model is already trained uh, with the image size or the spatial resolution of each image uh, of specific size. Meaning, what I'm trying to say is, suppose your model is trained with say 140 cross 140 ka image as an input image. One pixel corresponds to some meters in the ground. Here I don't exactly recall how much it is, say X meter. Since your model has already trained with that particular thing, rescaling images um, at the inference level uh, we might face some challenge. So either what we can do at first phase during training itself, we'll try to you know rescale our size or maybe resize your image and then train the model that way, so that in while inferencing we can have little bit lesser size image which can be managed uh, properly. Does that, I think, resonate with what you said?
I think yes.
Okay. Or was there any other thing that I didn't understand? You mean to resize the big image into smaller size, or like resizing small 140 cross
Miss,
140?
my question is that there is a different rows and columns in the images, so
Hmm.
we can rescale it in same rows and columns. So it's better to
Hmm.
analyze
Okay.
my
Okay.
model. Okay.
Okay. Okay. So you mean to say okay, but I think that is good suggestion. Now think about it that when you resize it, do you think that the spatial structure will lose some information in terms of, say, sometimes the spatial structure might get stretched, sometimes they gets compressed. Those
Okay.
kind of, right? Those kind of
Loss of
artifacts.
information means
Ha,
information may be lost.
correct,
Okay.
correct, correct. Yeah. To some extent, that will happen. So, but yeah, I mean, most of the deep learning workflow nowadays, we need to rescale it because the input size is of same size. So there is a trade-off that we can do. Okay, so now let's go ahead with the assumption that now we don't want to resize it. We want to maintain the information, and that's why this type of heterogeneity in the load or the workload is coming, and then we need to address that challenge. Okay. So now, if you try to recall the third challenge that I mentioned, right? So the first challenge was what? First challenge was runtime failure. We need to address the runtime failures. Okay. Second challenge was we need to balance or the resource utilization. If you remember the long tail curve. Um, the third challenge was very much specific to the Titan's scheduling policy. So here I will here and in the next slide, I think into the next slide I will talk about that third policy or the third challenge specifically. Here I think just in this slide I will give you some illustration. I just picked the two example images and I'm showing the dimension of the images just for the understanding. So basically, the graph on the right side here, then this particular cluster representation or the scatter plot representation of the data and this tabular representation are showing similar information in different viewpoints. So suppose you have these six clusters of groups of your images, and I choose two sample images from each of this cluster, and these are the number of rows and number of columns. So for example, cluster 0 has 35,000 cross 6,500 number of rows and columns, and this is this size range, somewhere around 400-ish megabytes. As opposed to if you look at the cluster 5, which is assigned to job number 5, uh, the size is 41 cross 46,000, 41K cross 46K, and their total size disk on the disk ranges around 3.6 GB to 3.7 GB. So just to give you similar information in different perspective. Um, okay, so now I think we will come to the third challenge soon in the next slide. But now you have understood that we have heterogeneity into the workload in terms of image size. Okay, and now we all understand that we don't want to use or assign all those images as one single job. So what we can do, we can distribute the job into different clusters, job clusters. Now this is what exactly is represented here. So you have one single image list. You do some sort of partitioning, data partitioning, and then you have multiple lists. For each individual list or image list, you create independent jobs. So as an IO approach, you can just use this one image list send to one job, one single job, as opposed to what we are doing here. We create multiple jobs. So based on, say, for example, here we have 6 jobs, job 0 to job 5. So we have 6 different job IDs, job 0, 1, 2, 3, 4, and whatever. And for each job, you will create a separate job submitter script. So in the beginning, I shown you a typical workflow where the scheduler is there. Before scheduler, there is a job, job submission script that you need to create. So this job submission script has typically a template that you need to create. And in that template, the things that vary most of the time will be the image or the path of the image or the list of the image that you want to process, meaning input, and then the location of the output where you want to store. Otherwise, here, job 1, job 2, job 3, whichever process is going to execute this job, these all jobs, they will have the same instance of the same but independent instances of the trained model. They have all the libraries and everything. They use the common installed libraries. So all other things are common and constant among all the jobs. The only thing that vary, what input it is going to process and what output, where it will going to be stored. So it is uh, sort of single instruction, multiple data kind of environment. Uh, in some other terms, it is also called as a embarrassingly parallel. Since each of the image list is independent of other image list, this job 1 has nothing to do with job 2. And that's how we tried to introduce better resource utilization. So if job 1 finishes earlier than job 2, then the resources or the compute nodes that those were assigned to the job 1 can be released. So now this is very generic mechanism. Whether you are going to use CPU multiprocessing, and in your CPU multiprocessing, suppose we are doing similar type of processing, then and those processes are say independent, then you can have this type of strategy. So from that scale to at the high performance computing system or the cluster scale, you can apply this strategy. Again, this is very basic strategy that one can adopt, but there are some other better solutions based on the so the novelty that can be added into this entire pipeline is the way you are partitioning. What could be the better way? The very basic way that we used was the size of the image, number of rows and number of columns based on that. But it is not necessary that lower the size. Uh, it the the image which has small size may take less time. Most of the time it is true, but suppose if one particular image has a complex structure or something, that image might take little bit more time to process. Meaning, if the image has more information, then it might take more time to process, as opposed to suppose it is a very desert kind of area. or desert kind of region where not much settlement is there. That means it might take little bit smaller time to process that entire. So based on the complexity of that particular image, what that image has, so if we can come up with some index that will try to capture in maybe unsupervised fashion, then based on that index also you can group it. That grouping of the images might be little bit more efficient than this naive grouping. So those type of uh, and this particular process is very much specific to this remote sensing data or geospatial data. So those type of strategies can be applied. Okay, so now uh, after, is there anything, any doubt or any question? Okay, yeah. So uh, I have been talking about this third challenge, right? This job scheduling policy or the constraint posed by job scheduling policy of the Titan supercomputer. Now, I will let you know that why this type of job scheduling policy uh, is in place for any with any this kind of shared high performance computing system, because it is shared among multiple users. Um, Based on the compute requirement, based on the number of nodes that you have asked in your job submission script, um, and a policy of fair share, meaning uh, you don't want you don't want to halt any user just because, or you don't want to postpone the execution of the job of any user just because that user has asked for more number of nodes, or that user has asked those number of nodes for longer duration. It's not fair. And also you don't want to postpone or give more priority to the user who has asked for fewer nodes, which might take couple of hours or maybe few hours. So only based on these naive rules, you cannot it you cannot perform job scheduling. So there has to be some different mechanism which will make sure that this shared resource will be shared equally among all the type of users with all the different requirements. So this is the job scheduling policy. So I will explain you some of the uh, information. So you can see that on the first column you have the bins. Okay, so basically bin number 1 to bin number 5. So we have 5 bins, meaning whatever job that it is being submitted to the scheduler, that job will either fall in one of those 5 bins. That is clear, right? And those bins are actually based on two main criteria. One is how many nodes that you have asked for, minimum and the maximum node ka bucket, uh, and for how much time you have asked for those computing resources. So let's say my suppose you want to execute your uh, Zambia or those 5426 number of images uh, in one particular job. That means you want to allocate 5426 nodes for your job. So you will request for those many nodes. So your job will lie in this bin number 2, correct? So your bin number 2 is here. And then if you are asking for those many number of nodes, maximum wall time that you will get. Wall time is you can get those many number of nodes between this particular range. If you are asking for, you can use those many number of nodes maximum for 1 day, meaning your processing can use those number of nodes only for 24 hours. For example, let's take another example. So if your job is asking for say only one particular node, your job is very simple and your processing is not very much costly. You will need only one node. So you'll request only for one node, correct? That means your job will fall in this particular bin number 5. Now, if your job is asking for only one node, the maximum hours that you will get that particular node is 2 hours. So it's slightly counterintuitive. What if your job might need like say 3 hours, not 2 hours? Then what will you do? Okay, so those considerations are there, and those considerations are actually uh, need to be addressed on at the developer level. So we as a developer need to make sure that we understand these type of policies, and accordingly you will adjust your schedule or job submission. Basically, the job submitter script that we have need to have some mechanism which will you know which will understand this policy, and based on that it will submit the job. Now, can you imagine what could be the artifact of this type of policies or the constraint? So imagine, I already gave an example. Suppose you are requesting for one particular node, and you know somehow that you will need say 3 hours to execute your data. But based on this constraint that was imposed, your job will get, or your process will get only 2 hours, or that compute node will be assigned to your job only for 2 hours. Then what will happen? So there are two possibilities. Either you can accelerate your job in some manner and try to basically make sure that your job will be finished within 2 hours. Correct? That is one strategy that you can do. You can use any mechanism, any optimization. You can do some CPU level parallelization and so on. Anything you can do. But let's say, what could be the another approach? Let's think about that. And you know that your job will need 1 extra hour. So can anyone share some thought in this context? What we can do? Suppose your job is actually such that you know that uh, even if you are asking only for one node, but your job is going to take 3 hours, somehow we know. What could be the another strategy that we can do to make sure that your job is also processed, and this particular constraint is within the context of this constraint, we will be able to process the job. What could be the another strategy that anyone can think of? So uh, again, I mean, let's keep thinking about it. In that thought process, let me add few more points. So let's assume that your job is now running. You have assigned one node. Your job is now running, and now during this runtime, since it is a very big system, lot of maintenance has to be done. There are a lot of failures. We cannot avoid those kind of failures. Sometimes we know the cause of the failure. Sometimes we don't know. Electricity failure, something may happen. Um, so when you run your job, three type of things can happen. One is either your job will be executed successfully. So it's a successful execution. It's well and good. We are happy that our job is finished within that particular uh, time window, and you were able to write your output. It's done. Good. Second situation may arise that there might be some runtime failure due to say node failure, something might happen, or say network failure while transferring the data, something has happened, GPU failure, etc. So this type of failure might happen. So because of those kind of failures, what will happen is you either your job is running, but something happened, so the job was will be terminated. And once the job is terminated, uh, your job will be removed from the scheduler. It's a complete removal from the scheduler. Okay, unless there are some other mechanisms that you have on top of the scheduler, or your scheduler is intelligent. But let's say scheduler is very basic, and now uh, termination of the job due to any failure will remove your job from the scheduler. So this is the second situation, correct? And then third situation will happen that there is no failure, but your job might get terminated because it will exceed the wall time. This is the same condition which I discussed earlier. So since you were allocated only 2 hours, but you know that somehow your job will required 3 hours. So that is a situation where the job might get terminated because of the constraint. Your job was actually um uh, must be finished within 2 hours. That was the constraint. Okay. So this is one thing. So these are the three different scenarios might happen. So now successful execution is good. I mean, but can we always make sure that our job is going to get successfully executed? We cannot guarantee that. Neither we can guarantee that our running execution will be failure free. Also, we cannot guarantee that our job cannot be finished within this 2 hours of limit. So while making this job submitter script, somewhere we need to account for this type of challenges. So are these challenges or the scenarios are uh, clear? I mean, are there any doubts or any questions related to this? Anything that we can discuss a little bit more? Or the question that I asked in this third scenario, what could be the strategy? Just to discuss. Are there any thoughts about those or anything something similar that you have used want to share? Okay. No problem. I think we can continue. But if something is there, if you recall, please share it. Uh, if it is different than what I'm going to discuss. Okay. So again, I mean, as I mentioned, highlighted that first situation is wonderful situation, but this second and third situations need to be taken care. So these two situations need to be somehow taken care. So what we did, so there is a concept called checkpoint restart strategy. Uh, so now this checkpoint restart has two specific terms. You might have heard about it, but just for the sake of continuity, uh, or to give some specific information in this context, I'll just define these two terms. So we have this checkpoint and then restart. So basically, checkpoint is something like a log or the partial output for that matter to be stored, or writing this log or the partial output to the persistent memory, so that in the event of the job failure, the processing can be resumed or restarted from the point of its failure. Is that okay? That this definition, you can provide thumbs up, or you can raise the hand also if you have any doubt, because understanding this is very important. Okay, so yeah, I saw one thumbs up. So yeah, that's good. So checkpoint is something, meaning your job is running and you want to write some log. That is our checkpoint. Okay, so that if it is failed, if that job is failed, then in the process of say restarting of the job, resuming of the job, you are not required to start from first point. You can restart your job or resume your job from the point of failure itself, so that you can save some amount of time, or you will avoid the wastage of your compute resources. That was the intent. And then restart. Basically, it restart is a algorithmic procedure, the step-by-step process that need to be followed uh, while resuming the failed job, basically. So that's how the checkpoint restart strategy is there. This is very simple definition, checkpoint and restart. But more or less, if you see in any of these HPC workflow or any of these tasks, when people do checkpoint restart, more or less the definitions are this. The only difference could be what type of checkpoint that you are writing. It could be a log, it could be a partial output in our case, because we are producing something. We are producing the output settlement map, right? We want that binary map where each pixel will have either 1 or 0 or something like that. So we want to store that map into the file storage that we have onto the Titan supercomputer. So, so again, one quick point. Basically, we are doing the processing at the compute node, right? So while processing, once the processing is being done, you need to transfer that chunk of output to the permanent storage. And that's what we can call it as a partial output writing into the persistent storage. Now, one more important thing is you can write some log also, uh, which could have some metadata or ancillary information. Very simple example is what column and what particular row, what was the column number and row number of the image, of the entire image that was processed last time successfully. Successfully meaning you have written the data also. So you need to make sure that your data was written uh, without any error into the persistent storage, and then you will mention into the log that okay, um, this was the row number and column number which was processed last, which was successful, and you were able to successfully write the data. So that was one example of the log. We were also doing something similar, but it could be somewhat complex also based on the application. So now you try to relate the this checkpoint restart definition with the question that we posed. That suppose your job is now going to fail after, say, your job is going to be terminated after 2 hours, even if there is no runtime failure. What we can do? So this is the solution. We need to have some mechanism in place which will write the checkpoint while the job is running in that 2 hours of window, and once the job is finished uh, or terminated because of say 2 hours of wall time limit, there has to be some restart mechanism which will identify or detect that okay, this job number XYZ was running so far, but suddenly there is no record of that job into the scheduler's list of the running job, but it is marked as completed. But I see that the job is also tagged in the output log as incomplete, meaning the log, the ancillary information that you are storing, it says that it has not completed. It was not tagged as completed. Okay, so when the steps that you follow into the restart mechanism, or specifically into the job submitter script basically. Okay, so that job submitter script, this restart mechanism will basically try to see whether a particular job, when it is marked as a complete, whether it was actually complete, whether it did finish your job or not. If it has not completed, then there has to be some mechanism which will resubmit the job, maybe the next level or the next version of the same job. Um, but now, since you already have written the log and you have restarted or resubmitted the job, when the scheduler will schedule that job to some other node, it will not resume, it will not start from the beginning. Now, since you know that from where to restart, you will directly jump to that location onto the onto the remote sensing image, take that chunk or the tile or the batch of the tile, and then start processing. So that was the the whole story behind checkpoint restart, addressing the failures, runtime failures, then um, addressing that long tail effect and so on. So this was one of the strategy. So in our case, to be very specific, in our case, we write the partial settlement map. Very simple sense, it's a matrix of x comma y dimension. Whatever information that you have processed, you will have either 1 or 0 at that particular pixel location. Rest of the pixels will be, say, negative value or not a number kind of information. Okay, so as soon as you finish one particular chunk of those small image tiles, a batch of image tiles, you will write the output into the uh, permanent storage. So during runtime, you will also make sure that your partial settlement map is getting updated during runtime. Okay, so is this particular thing is clear? Now, are we all able to visualize the challenge that we pose during runtime, the challenge that could occur, and how we can overcome or address this challenge? Are we able to make connection between them? Nice, nice. Any thoughts or any comments? Specifically, I would like to know. I would like to know uh, your input, as in uh, specifically, say when I say that I write this checkpoint, right? So what could be another form of checkpoint? Let's keep thinking about it. What could be the different type of checkpoints we could have used? Right now we have used very basic first version of solution where we write the partial output, right? But there could be something else that we can do. Um, so when we are writing, you try to imagine that you need to transfer the data from compute node to say storage node. So there will be some amount of risk that while transferring the data over to the network, there might be some failure also. Okay, so we need to make sure that then there might be some so while transferring the data, maybe your GPU will be idle for that amount of time. So those kind of challenges are there. So maybe some other strategy like you can use the pipelining where you will write the data, you will overlap that uh, process, you will overlap that writing process with the processing of say next batch of image tiles. Those kind of strategies can be done. So let's keep thinking about it, that what could be the other ways we can write to make it our life easy, instead of or make it more efficient. So that is very important point. What So that is one thing, that what type of log or checkpoint you want to write. Now there is second question that I would like to ask or rather discuss. So if I tell you that you are going to get 2 hours, okay, and your job is going to run for 2 hours, should we write our checkpoint or the log at every 10 minutes? What could be the best frequency? Should we write at every 10 minutes? Should we write at every 1 hour? If we write at 1 hour, that means there will be only 2 logs. What will happen if our node fails at 30 minutes, right? What will happen? That means you don't have any opportunity to write the log. But if you have written the log at every 10 minutes, you might have say 60 logs or 6 logs or something like that, close to 6 logs, 5 or 6 logs. Before it fails at say, no, I think close to 3 logs before it fails at 30th minute. Um, so, but okay, so the question is, what should be the frequency that we should write? So that is the second question. First question is, what could be the output that we can think of? Then second question is, at what frequency we should take the log? Now I will give you some, I will shed some light on that particular aspect. So we know that saving this intermediate output is very important, but at what interval? So for example, suppose this is the run, your job is running, and this triangle represent checkpoint. Okay, nice. Yeah, I think Ms. Dipti is saying that intermediate log would be good. Yes, so exactly. So meaning we need to take the log, that we all agree. Now, at what frequency? Let's say these are the two scenarios. So for example, this first scenario is you're taking the logs too frequently. Means at every 10 minutes you're taking your log. As opposed to you will take log at every hour. Okay. So now there is not a very good strategy, very bad strategy. There has to be some trade-off. But before moving to that trade-off, let me tell you what will happen. So if you take the log too frequently, it will be an overkill. Means you will spend more time in transferring the data than computing. Do you all agree? Just give me thumbs up so that I will get the acknowledgement. Okay, correct. So basically, if you take more frequently, if you take your log or checkpoint more frequently, the overall it will slows down. Overall job will be slowed down. Correct. And then, but as at another extreme, Suppose you are taking the checkpoint, or you're writing your settlement map at say at very sparse interval, say at every hour interval or so, something like that. So what could be the risk? So if your checkpoint is very sparse, then there could be the risk of data loss or during due to the failure. So more risk is involved here. Here in the first case, the risk is low, but it will slows down the entire job. So that's why the trade-off. There has to be some trade-off. So that situation arose when I was working on this. So then I tried to find out, is there any formula or was there any work which will tell me what could be the optimal checkpoint interval. And this was the work done by Dial in 2006. This basically this work was actually uh, addressing this specific problem, that in HPC kind of environment, failure is bound to happen. Now, at what interval one should take the checkpoint, basically. So this is the formula. So this T optimal basically represent the optimal checkpoint interval. So we just need to calculate this. So this is a function of delta and m. Only two variables are there, delta and m. And then once we have the value of these two, you will plug it here, and then you will get the optimal checkpoint for the process that you're running. Okay. So this delta is basically time to save the checkpoint, and m is mean time between the failures. Okay, so these are the two important points that we want to understand. So this we know, this T optimum is know, which we want to calculate. This delta is time to save the checkpoints, meaning when you initiate the checkpoint at the compute node and when you transfer the checkpoint on the network, when you write the checkpoint, this entire time is called as a delta. How much time it takes to write to save the checkpoint. Okay, so you may ask that why this delta is variable. Yeah, I think there is some question. Yeah. Okay, so I think the point that I wanted to make here is why this delta could be variable. Why it's so variable? If you are running same job, then it might take the same time, right, to store, because the network will be same, and we can assume that network is same and everything is same. Let's assume that the amount of data or the checkpoint data size is same. It will be, say, X amount of bytes that you want to store every time. It is a fix. I agree. But the network over which that independent chunk is being transferred to the storage, that network is shared among different jobs. So it is shared among different jobs, some from another user, it is shared among some other activities, and so on. So when one particular uh, node or the process of your job is sending the data, it might take, say, some millisecond, X amount of millisecond, but some other process which is executing some other node, which is physically located in some other cabinet, from there, if it is trying to transfer the data over the network to the storage, it might take some different time. So this delta is variable. Are you able to visualize the scenario? Do you agree with this? With this argument that I made, that this delta will be variable and it is not going to be same for all, or the constant for uh, all the checkpoints that your processes are going to write, because of the main reason was what, it is going to be transferred over the shared network to the storage. Now, this point, this time you can compute. So as soon as you write first checkpoint, you will do time dot time, and you can, for example, in Python we write time dot time, right? So you can compute, you can mark the start time after writing the checkpoint successfully. You can again measure the time, and you can take the difference. So at very first time, you will try to find how much time it is taking. If you repeat it for 2 3 times, you will get an idea of how much average time for me, meaning I am the process P1, for how much time I'm taking to write the checkpoint from this particular node where I am assigned to execute this job, how much time it is taking to transfer the data and write the checkpoint. Maybe processor P, it is different. So initially, when you write the checkpoint, maybe you try to observe it for initial first few checkpoint and then try to take the average. So that's how you will obtain this delta, and this delta will be different for different processes. Now, then this another constant is called mean time between failure. So this mean time between failure is sort of constant actually. Now, as name suggests, what is the average time in a given high performance computing facility between two failures? So how we can compute? So this we cannot compute while running the job. This is something that the company which is maintaining that HPC system, they basically scrape the logs of all the previous or the historical logs of the jobs which were successfully executed, which were failed, and whatever. Okay, and they try to find out this one particular value. So for Titan supercomputer, I was lucky enough to find this particular time for Titan supercomputer. So for Titan supercomputer, based on the historical log information, average uh, this mean time between two failures was approximately 28 to 29 hours. So uh, at exactly, at every 29 hours, we have, failures. So I had this information, and then we were able to compute the checkpoint. So that's how we obtained the optimal checkpoint. And I think I will skip through this. You got the idea, overall flow, but we can skip through this just in the interest of time. As a last comment, based on this particular checkpoint, I'll just try to, show you some example. So this is how we, and then I'll wrap up. So we can take some, questions if you have. So basically, we know that we have these 6 jobs, right? Now you already know that either that job can be finished in successfully within 2 hours, or that can overshoot the 2 hours of time limit, or there could be some runtime failures. So this job zero, if you remember from the that colorful clusters, it had smaller size image, and then you can see that when the job was submitted, this is a timeline that I plotted here, and triangle represent the checkpoint. I took one checkpoint, and this first line, these lines represent two images basically. I just took the timeline of two images when they were being processed. So this is the time when we took the first checkpoint. This is the time when we took the first checkpoint. But fortunately, that job was able to finish within 2 hours. Now take the example of job two. This is the exact situation which we thought. Throughout the runtime for the first 2 hours, the job did not have any failure, but there was a termination representing the end of the job, and that was when the job was terminated. It was not completed the job. This job was restarted, and then this job was resumed from the last checkpoint, and it was finished within, say, next 15 minutes. Then the another scenario is job 5, where we have the similar situation, and again job 5 images of larger size. So even if there was one resubmission, here at this point some failure happened. We actually simulated that no failure. We terminated the job forcefully, and then the job submitter module that we have, it recognized that situation, and then it resubmitted the job again from the failed checkpoint, from the previous checkpoint. So only this, some amount of compute hours was lost. But after that, when the new job was submitted third time, then it was able to finish within one more, again there was some one more time there was resubmission, and it was able to finish it. So basically you can see that job number 1 0 to job 5, all 6 jobs are, independent. And once the job 0 is finished, the compute nodes were able to reallocated or reassigned to some other, node. So this was the whole idea behind, the uh, your better resource utilization, addressing the failures, runtime failures, and so on. So this is how we were able to, process the entire all the images of this Republic of Zambia, which is spanning around this much of kilometer square. within almost 6 hours. So that entire, this entire timeline, if you start from beginning to just calculate the entire timeline, we were able to finish processing these many GeoTIFF images within 6 hours. So that was the achievement that we did that time, and we were able to provide the output. So this was the main, content of the today's presentation. So if I know that I overshot in the flow, but yeah, I think we had good discussion. So I can take few questions if time permits. Again, apology for overshooting the time.
Yeah, yes, it's okay, no problem, sir. Yeah. Thank you, Dr. Kuldeep, sir, for sharing your valuable insights with us. And it was really very informative session. So we'll have some question answer session right now. Participants, please feel free to ask any questions if you have. Till then, I have one question asked to me. How can parallel processing helps in multimodal data set?
Okay. So the question is, how can parallel processing help in multimodal? So one or two example of it.
Like probably if there are, because
Meaning
in
example of
each
multimodality.
modality there are different pixel sizes, no?
We can let's assume that we have. So I think there are two parts basically how parallel processing can be used, right? So one thing is uh, so if you recall this particular flow chart, yeah, this one. So when you distribute, so one point is when you distribute this job, you typically tend to use MPI kind of environment, message passing interface, that will be used to distribute the job. Uh, but then if you want to go one step further, and you want to take advantage of GPUs, then GPU computing is another thing that you can, which is called as heterogeneous computing, where you basically try to, mingle CPU processing with the GPU computing. So that is one thing. Now, when we bring in multimodality, just to be consistent with the question, I assume that let's say we have two different types of data. One could be image data, one could be audio data. For just an example, uh, assuming that uh, assuming that two data sets are two modalities of the data are independent. If that is the case, then either OpenMP processing those type of data, if they are independent, then this type of message passing interface where you distribute the job among independent processor can be useful. But I'm not able to recall any specific method where you can, use MPI or OpenMP kind of mechanism where you try to, process those two modality of the data together. Yeah, that was, I think, my quick remark on that.
Yeah, yeah. Okay, sir. Thank you, sir. So one more question, just wanted to ask you about, can you specify any open source tool for this scheduler job scheduling part, like
So
challenges with?
one thing, yeah, I think that Slurm thing I told you, SLURM, Slurm, is an open source tool. I'm not sure, I think, which, but if you search, you will get the um library in any C library or something, C++ library we can get, and it is useful for any HPC environment. That's the open source that we can use and you can install. So if we have any small cluster facility, wherever there is a login node, typically people tend to install that slurm at the login node because that's the point where the slurm will be distributed. That is the one thing. Yeah, that is one open source library that comes in my mind. Otherwise, I think in the context of libraries, uh, OpenMP is there, and then MPI. MPI libraries, those are the open source libraries which are available. But there are some other libraries that comes with Intel. I mean, Intel has optimized their MPI and OpenMP, uh, and some of them are freely available, some of them are licensed or something like that. But the basic, I think the free version is also, I think, useful for our job. If we just search MPI, we can get libraries and all.
Thank you, sir. So now it's like we are end with the. Yes, anybody wants to ask any questions?
Uh, Hello, sir. Is there any pre-trained network for geospatial image analysis, like VGG 1619 and Yamnet and PAN for music? Like any pre-trained network
Hmm.
available?
Yeah, so basically, most of these backbone networks, so I will just give you brief answer. So basically, most of the ImageNet pre-trained networks, right, VG16 or ImageNet, whatever, ImageNet dataset pre-trained network, those networks were largely adopted to the in the remote sensing domain, and they were either fine-tuned for the remote sensing data. So, very recent network that I used for some of my work was called as a Deep Solar Plus Plus. So this Deep Solar or Deep Solar Plus Plus was actually fine-tuned for the rooftop PV detection task from satellite imagery. So given the satellite imagery, uh, if the task is to identify the rooftop solar panels on the building, so for that this particular network was customized and they trained it for different building rooftop images for US. So that was one network that comes in my mind. There is one more network, uh, uh, Big Earth Net. So there is this group from Europe which works and they basically try to train generic networks um, for the remote sensing data. So their network is called as a Big Earth Net, and I think they have their TensorFlow Keras version as well as PyTorch version is also available. So Big Earth Net is there, and recently the clip model, the transformer based architectures, the clip model is there, which was trained on the ImageNet dataset and ImageNet and caption dataset basically. So this transformer based architecture was adopted for remote sensing data. So if you search for clip ISCD or ICSD, clip ICSD, and remote clip. So these are the two recent model which were trained for remote sensing data. So those are the few models that comes in my mind.
Okay, sir. Okay, thank you, sir.
If you want to find their so Hugging Face is the library that you can look for. So basically, this is what it looks like. Hmm. So Hugging Face. So Hugging Face is the repository where you will find. So maybe you try to search for say remote sensing model or something like that, or whatever task that you are doing. Try to search. You will most of the time you will get a pre-trained model that was developed by some big organization or some um uh, through some projects. They made it available or free. So this is the platform
Yes.
where you can download. Yeah.
Thank you, sir.
Yeah.
Now it's time to express our sincere thanks to our eminent speaker, Dr. Kuldeep Kute sir, for his insightful presentation on geo high performance computing and geospatial big data and advancement in geospatial technology, as well as job scheduling challenges in supercomputers. Thank you, sir, for sharing your valuable time.
Yeah.
And sir,
Thank you
we
so
truly,
much. Yeah. Thank
yeah,
you so much for invitation. It was always great to share the little work that we have done in the past, and the crowd was very much, involved. That's how I think we exceeded the time, few minutes.
Yes, sir. It was really interesting session, sir.
Yeah.
So, sir, we are truly grateful for your time and expertise that you have shared with us. Your session has given us a lot of things about the various aspects and the applications of high performance computation. Thank you once again.
Thank you so much for the invitation. Yeah. Have a good day.
Yeah,
Bye.
thank you, Kuldeep, for the session. Yeah.
Sure. Okay.
Thank you, sir. Yes, participants, we have end with the session. So tomorrow, sharp at 6 p.m., we will start the next session. Okay. So all of you, please be on time. Thank you so much.